ನನ್ನ ತಮ್ಮ ಅವನಿಗಾಗಿ ಏನು ತಗೊಳ್ಳಲ್ಲ, ಅದಕ್ಕೆ ನಾನು ಅವನಿಗೆ ಇದು ಬೈ ಮಾಡಿದೆ. ಅವ್ನು ಯಾವತ್ತೂ ಕಂಪ್ಲೇಂಟ್ ಮಾಡಲ್ಲ, ಆದರೆ ಎವ್ರಿ ಡೇ ರೂಟೀನ್ ಬ್ಯಾಕ್ ಪೇನ್, ಗ್ರೋನಿಂಗ್ ಮತ್ತು ಬೆಡ್ ಎಡ್ಜಲ್ಲಿ 10 ಮಿನಿಟ್ಸ್ ಕುತ್ಕೊಳ್ಳೋದು. ನಾನು
noise cancellation आपला
सेम ऑलरेडी स्टार्टेड करते हैं.
check.
Good morning to one and all present over here. It gives me immense pleasure to warmly welcome all of you to the 5th day of ATAL Faculty Development Program. We are truly delighted to have such an enthusiastic gathering united by shared interest in learning, innovation and academic excellence. Today's session is made even more special by the presence of an eminent academician, researcher and a mentor, Dr. Mohammed Riyaz Ahmed, whom we are honored to have as our resource person. Ladies and gentlemen, let us have a huge round of applause to our resource person. Dr. Mohammed, let me introduce our resource person for the day. Dr. Mohammed Riyaz Ahmed is a distinguished academician with over 12 years of rich experience in teaching, research and academic leadership. He is currently associated with HKBK College of Engineering as principal and has previously served at reputed institutions including Reva University, Bangalore. He has held several key academic positions such as Head of the Department, Assistant Director, BOS member and Academic Council member, contributing significantly to curriculum design and academic governance. Academically, Dr. Riyaz holds a BE in Electronics and Communication Engineering, an MTech in Computer Networking, a PGT BA in HR and Business Administration, and a PhD in Reinforcement Learning. Notably, he has also been accepted for a visiting postdoctoral fellowship at the Cybersecurity Lab, City University of London, UK, which stands as a testament to his research excellence. Dr. Riyaz has taught a wide spectrum of core and advanced subjects, including circuit theory, control systems, CMOS VLSI, microwave, and RF communication, and emerging areas such as artificial intelligence, cybersecurity, design thinking, and engineering innovation design. He is deeply involved in mentoring students and has successfully guided numerous undergraduate, postgraduate, and doctoral research projects, resulting in award-winning outcomes. With over 100 research publications, multiple national and international patents, and active involvement in consultancy and funded projects, Sir continues to make impactful contributions to academia and society. He is a senior member of IEEE, life member of ISTE, member of IETE, and an executive member of the IEEE Education Society Bengaluru chapter. He also serves on national and international steering committees, including TAIL 2024. We are extremely fortunate to have such a distinguished personality with us today. On behalf of the organizing committee, I extend a heartfelt welcome to Dr. Mohammed Riyaz Ahmed, Principal HKBKCE, and sincerely thank him for sparing his valuable time to share his knowledge and experience with us. I kindly request Dr. Tabassumara, convener of this AICT ATAL Faculty Development Program, to kindly present a token of appreciation to our principal. Thank you all, and I hope today's session will be insightful, engaging, and inspiring. Over to you, sir. Yeah, it's there. Tell myself, both this side.
Check. You will record everything, right, sir? Everything. No, only this one. I'll give in 5 minutes. We can start. Fine. Good morning.
Good morning, sir.
One advantage of giving our brief biodata 5 years older so that it will save time. I have almost 17 years of experience, so 12-year experience means the biodata is 5 years old. Anyways, we have been, as Tabassu Madam said, we are seeing the quantum of quantum, not the entire quantum. you have been briefed about quantum engineering, quantum computing more precisely. In the last few days, you have been bombarded with all the beautiful, amazing terminologies such as parents and all these things. So I have been preparing notes for this, and this is, yesterday night I prepared 4th version of that. So again I brought the 4th version of that. If the session was tomorrow, I think you would have seen the 5th version of that. Because when we don't know what we are doing, that is where required? What required? When we don't know what we are doing, I think that is defined as research in a rough way. First, my approach was to have arguments about Einstein, Niels Bohr, and Heisenberg's concept towards reality. And that was my first approach even before the FDP started, and the notes was according to that. But later I realized that I am not so qualified to contemplate and also criticize the theories what they have been given. And with the confidence what Richard Feynman said, if somebody says that I understand quantum mechanics, that means they declare they don't understand quantum mechanics. So I thought that's a wrong approach. Then when I sat for the first session on the day 1 with the inauguration and all, then I thought that I will give a brief history and also future trends, challenges, and where exactly the energy is deviated in quantum research. And that was also one version. Then day 2, when I sat for the session of Pallavi Sure, Dr. Pallavi Sure from MS Ramaya, one of a great eminent personality in the area of quantum, IIT Kanpur alumnus. After seeing the fundamentals, what she said, I felt that much of the mathematics is covered. So theory is not required. Then I thought we will cover mathematics, and day 2, madam covered most of the mathematics. And the flow what she has given, I might give a different flow, but she has done the best. So I thought I will again revise the notes. Then 3rd day I didn't attend any of those sessions. I was completely fixed with the commitments of check. Yeah. So I didn't revise anything. And then I saw 4th day. Let me give a brief analysis of how the evolution happens with only 20 to 25 minutes dedicating for that. Later, I saw the real question of faculty. If I have attended FDP of quantum engineering, my first question will be, okay, I am amazed. Wow, quantum is a new era, it's a new domain, and now I want to have everything in the realm of quantum, and I want to redefine everything. If I am a PhD student, I want to redefine my objectives into quantum. Okay? For example, if I am working on machine learning, I want to redefine one of the objectives, or if I am an aspirant PhD, then I want the complete discussion to be of quantum machine learning. Okay? So I thought this perspective will help you how to do research, and I'm not going to explain what are the trends because the trends are changing every day, and you have been hearing from the various resource persons what are the trends of that. So what I will try to do today is, I will give you few brief conclusions what we heard in last 4 days, and after that we will start building on a problem statement, and we will take a problem statement of normal machine learning, and we will build the entire stack of it, and then we will take that objective into quantum domain. Again, we will rebuild the entire objectives of that, and we will build the stack of that, and that is how we completely redefine that. With this, you will be capable of writing a paper on your own, or with this you will be capable of working out a quantum small gate or a circuit with the students in the lab. With this, you will be capable of even guiding PhD under quantum domain. So it will be completely hands-on. Don't expect fancy PPTs. Even one PPT I have, I can share it for you, and also have materials which will be shared with you. But let me tell you, I will make you to write much today. We have to write many things today. So that's why I requested organizer to inform you all to bring 2 to 3 pen and pencil bhi agar ho gaya to acha hai. So today it is not development program, it will be workshop. We will be working together, and let me tell you, if we are together and if we maintain time, if we respect the time, I am sure that by 12:15 we will have a complete title for a PhD, objectives defined under quantum, and how to write the paper and what all things will change in quantum realm. When you write the paper from machine learning, migrate it from machine learning towards quantum, what all things will change, how the methodology will change. These are the things which will help you in real time. The problem is, yesterday I understood a few registrations who have done, one motivation is to understand quantum, and more than that, I am doing already, I have registered for PhD in quantum, or I am migrating one of my objective towards quantum. Now how this FDP will help me? So I reworked on that completely. So let us go with that flow. Okay, am I clear with that? So here are some materials which I thought I will discuss for 2 hours, but within 20 minutes we will wind it up. This side. Just keep it with you, don't turn all the pages. This is the mistake what my students do in examination. In examination, they read all the questions. First 1AB, 2AB, 3AB, 4AB. The next moment they start saying, I know this, now I will get 8 out of 10. They start evaluating even before starting the answers. So please wait on the page 1. You people are comfortable, right? You can see it right now. Done? Okay. I am not a true physicist, I am just engineer. So using that, engineer means chalti ka naam gaadi. Is it working? Good. It will come in the syllabus. Is it commercial? Good. It will come as a startup. If it is not working, it doesn't come as a startup. If the theory is wrong or mathematically not proved, it doesn't come on the syllabus. If it is proved as a theory, it will come in the syllabus. If it is commercially viable, it will come as a startup. So I don't want to dwell into more deep of quantum because you have heard many people, and I am not qualified to go for physicist level of explanation. But every day, if I want to travel from point 1 to point 2, from point A to point B, I can walk, I can ride a bike, I can go with bicycle, I can go with car, or maximum I can go with a bullet train. Okay? So these mediums are helping me to increase the speed, efficiency, comfort. They will take care of speed, efficiency and comfort. Now, if you want to go to an unknown terrain, these are the known terrain. You know location A, you know location B. Suppose, for example, I want to go to Antarctica. Suppose I want to explore where is India, Vasco da Gama. Then he cannot do it on bicycle, he cannot walk. He cannot go with car, he cannot go with train. He can go with ship. Ship will help you to go to unknown terrains where all other vehicles stop. You cannot ride bicycle on the ocean, you cannot take car on the ocean, you cannot take bullet train on the ocean. Now this is where quantum comes into picture. If there are engineering problems you are solving with classical engineering, with classical machine learning approach, with classical physics approach, then all the problems can be solved. And when you end up with NP, non-deterministic, for example, I will give you a small example of deterministic and non-deterministic. Suppose this is the location A, that is the location B, the force applied on this, the displacement will happen. Force is equal to mass into acceleration. In between, what if I leave it? It will fall down. It is non-deterministic. So, you assume that it will go from position A to position B, you know that, and that is why you have classical physics which is sufficient. The Newton's law are sufficient for you to analyze those things. The quantum will come in a place when the system is not deterministic. It is NP problem. You might have heard NP. NP means, I also googled what exactly is NP. Non-deterministic, where you cannot determine the outcome. It may fall. And we don't know how many pieces it will happen. And if it is filled, the momentum is different. If it is half filled, the momentum is different. So if you cannot determine the outcome, that is where you need to have quantum engineering. A simple example I will tell you, one more with the level of physics. One way of measuring the dimension of this room. How do we measure the dimension of this room? Length into breadth. So we are completely into classical domain. Imagine if you ask the same question to quantum, it will enter the room, the quantum bit will enter the room, it will bombard with sound, take the echo, based on the echo profile it will tell what is the room size. Yes. So when we go to that level, now I am in still 2 dimension. I am in still 2 dimension. I am talking about only voltage wave, current wave. So when you go with the classical thing, you have a small set of deterministic thing where you can determine the space of this room or the complete volume of this room. But if you want to know with very random way and you want to know without any engineering aspect, you want to allow the physics to take care of it, then quantum will come into picture. Okay, so ship is one way where it will help you to explore continents where you don't even know the terrain. So quantum is that ship. Don't mistake that quantum is another way which will help me to travel with more faster train. No, CPU is different. CPU, GPU, all those things are product of your classical physics. When we first took the circuit theory, we applied Ohm's law, V is equal to IR. We applied Ohm's law and we saw that the power is product of voltage and current. And by this, we started to contemplate engineering solutions out of that. And when we got this, it split into 2 domains. One is, we tried to make logic gates out of that. Okay, first we made small amplifiers, okay, and then we converted into digital domain. This is digital domain, and then this is analog domain. In analog domain, I had op amps, okay, a simple diode, a continuous diode, a transistor, they all come here, okay, diode, transistor. Once you convert that physical operation into digital, it becomes switch on, switch off, and that analogy will be taken in digital domain, it will become gate. Now these gates, when clubbed, they will become combinational circuits, right? And when these combinational circuits are designed, are planned, are scaled, they become processors, microcontroller, microprocessors. Okay, and when these microcontrollers and microprocessors are used for application specific, then they become embedded system. So all this time we were in the domain where only 2 domains were there. One is voltage, one more is time axis, or one is current and one more is time axis. Suddenly there was a limitation when we started operating beyond 2 megahertz. And when we started working beyond 2 megahertz, we only thought that the lumped parameter extraction, the lumped parameters such as R, L and C, for any flow of current, the resistance will be one part, the inductive reactance will be one part, and the capacitive reactance will be one part. This was our limited knowledge, and that is why they keep electronic circuits to CS students also, because they should know only this much, voltage and current. But unfortunately, if you have taken electronics as a subject, then you will be welcome to a new dimension, 3rd dimension. Okay, the max will come into picture and you will be welcomed with these notations, and you will be not only going with V, I, R, L, C, you will be going with E, B, J, mu, epsilon. Okay, this is very important and it is part of quantum, believe me. Right? So when you have electric field, magnetic field, you have permeability, you have permittivity, this is a new dimension. The Ohm's law stops there. Ohm's law is not applicable here. कैसे होता है? For example, when you have a circuit and you transmit that, and the moment you transmit, it is no more 2-dimensional, it will be 3-dimensional, and in 3-dimensional there is no conduction. There are only waves. That is where we explored the wave nature for the first time in physics, when Hendrik Hertz said that I can shoot wave via a electrical signal through a open-ended wire. A open-ended wire is a simplest antenna, and this antenna is a transducer. It converts two-dimensional electric wave into three-dimensional field waves. It will create a pattern. So from 2D, when we migrated to 3D, we got new set of applications. Now do we say that this new theory, this theory is called as field theory? If I say field theory will replace circuit theory, it is wrong. Circuit theory is an abstract of, are you with me? Yes, sir. Nashta heavy agide na? Circuit theory is a subset of field theory. Circuit theory is a subset of field theory. This is circuit theory where below 2 megahertz everything is valid, V is equal to IR. But when the field waves increases, here I don't only see resistance, I don't only see inductance, I don't only see capacitance, I see some phenomena beyond my understanding. They are permeability and permittivity, and we see the flux linkages, and there are magnetic fields. And these magnetic fields are not conductor, insulator, semiconductor, they are not dependent on that. They are just dependent on their free will to travel in the 3 dimension. Now, field theory will come into picture, and that will give new notations. There are new operators. There is a dot operator, there is a cross operator. So these are the new things which come here: dot operator, cross operator, okay? And then you have all these new notations of electric field, magnetic field, you have permittivity, you have permeability. So this is a migration from 2D electronics to 3D electronics. Now with this, what all we did? We achieved communication, we got 2G, we got 3G, we got 5G. So this new domain did not replace this, but our understanding to electronics has increased. Okay, with field theory we got microwaves, now we got radar. Now I can measure the room size with a radar, sir said, right? So instead of going with length and breadth, I can have an instrument which will just bombard the signals and get the signature of this room. According to the signature, it can guess the size, volume, including pollution, if you have such sensors. And you can see the occupancy, you can see the carbon rating of this room and content of that. Whatever sophistication you can add here in this domain, not in that domain. This is just like you are transforming from one domain of physics to another domain of physics to understand more. Now, here you thought that if electron is flowing, then it is, if it is off, it is 0, if it is on, then it is 1. In Maxwell, if the field is there, and the field are regenerating, E and H, if they are regenerating, then it is on. If the field is not there, then it is off. Now, we went back one step behind. If electron is moving, how it is moving? Is it spinning? What is the phase? What is the wave function and amplitude in that wave function? That is quantum. So it is not new. Our vision has increased. Our vision has increased. पहले हम क्या देखते थे? ऐसा करके देखते थे, करंट लगा तो करंट फ्लो हो रहा है. Okay? Then we saw that if I transmit through an open-end wire, there I am able to receive the signal. So it's a 3-dimensional. Now we went one step back. Electrons are flowing, waves are happening. But what electron has data, what wave have data? Whether electron, we started arguing whether electron behave as a particle or as a wave. I am an engineer, whether it is up to electron to behave as particle or wave, मुझे outcome चाहिए. Measurement में I need a outcome. Okay? It is job of physicists to decide whether it is behaving as electron or wave. For me, what outcome comes, accordingly I will commercialize that. I'm an engineer. Okay? So when we take this line of argument, we see that the electron has more to offer. If it is flowing on, if it is not flowing off. Usse bhi pehle, electron is there, that itself is information. There is an entropy in that. It has a knowledge in that. This electron has a spin, that is one information. If it is spinning in this way, so this is quantum. If it is spinning in this way, if it is spinning in this way, there is a information. Do you agree with me? I am not telling anything new, quantum. Electrons will spin in this way, right? We used to write azimuth number. Now, if you know that it is spinning in this way, do you want to measure or you want to guess that it is spinning in this way? If you know one electron is spinning towards north in a 2s shell, hydrogen atom with the atomic number helium, you take helium 2. One electron is spinning towards north, then obviously second atom will be spinning south. Entanglement. So if you can find the spin of one electron, you can tell the spin of its entangled electron by default, without any measurement, without any engineering. You can just be a nomadic person, and if they say that this is the spin of this electron, you can easily guess this is the spin of another electron. This is entanglement. Artha aita? That also doesn't mean that this is nucleus. Electrons will never, they will create a cloud here and they will be spinning here, they will be spinning in this way. And if this is spinning in this way, this will be spinning in this way. But you cannot say that it is always spinning in this way. It can also spin in this way. Go away from nucleus, fall near the attraction, again repel with the nuclear force, again go back. We don't know. And if it is going in this way, it is going in this way, this is entanglement. Whether it is spinning in this way or whether it is spinning in this way, until we measure it doesn't show. That means it is in superposition state. Okay? Whether the electron is spinning towards up or down, right or left, clockwise or anti-clockwise, I don't bother. But if it is spinning and another electron is complement to that, I can guess it easily because it is entangled. It is entangled. And this electron, which is free to move, it is not defining its spin always. That's why I say, if it is in this way, then this will be in this way. It can immediately change, it can change at any time, it can collapse to any state. So it is already in superposition state, whether it is spinning north, whether it is spinning south, but there is a possibility of anything. And that is called as superposition. So when you go back here, now the electron also has phase. If it is moving, it will have phase. Okay, if it is spinning, it will have angle. And if it is moving, it will have magnitude. That's why you were deriving the wave function always, the psi. The psi may alpha and beta are the amplitude of the waves. These will tell you some information. The phase will tell you some information. The angle of the sphere, the imaginary sphere, they always used to show whenever there is a quantum discussion, the sphere is there, this sphere is there, and one line is coming out of that. So that also has again one more information. And the information are not independent, they are entangled. So this we have exploited, and that is why we are in the quantum realm. So with this quantum, we are not going to replace our circuits. We are not going to replace our microprocessor and microcontroller. We are not going to replace our embedded systems and CPUs. CPU, GPU, all those things. We are not going to replace our accelerators, but wherever classical engineering stops, quantum engineering starts, and it will come into picture and it will provide the solution. But quantum engineering is very natural way where you don't need to do engineering. The physics will do on its own. Simple, for example, if you hide a ball in this room, now I have to go one by one or nearest to center, any of these algorithms will help me to go towards that. But quantum, what does it do? It will push the water in the entire room so that the ball floats here to my floor. So that is, physics will give the answer, you no need to search there. So that is how quantum does. Quantum use all the abundant physics and it will give you the answer. The moment you are observing, it will collapse to one outcome. Whether the ball is there, whether the ball is not there. Okay? If you go with classical, search, binary search, even search, odd search, half karke, beech mein jana, all those things, algorithms which we used to write C++ programs, right? That is not required. It will flush the complete room with ball so that the ball comes near to the questioning observer. and they will say whether the ball is there or not. So that is how quantum works. And it is more efficient because it is more true towards physics. You are not using the electron to store information, you are checking the information stored in the electron. So it is very, very energy efficient. So that is what I have discussed in the second page of the content, circuit theory to field theory. The evolution is circuit theory to field theory, and if this is a circuit diagram, circuit theory and field theory, let me tell you, this is classical engineering and this is quantum engineering. If you say classical engineering is wrong, then you are also saying quantum engineering is wrong. It is a subset of that. Okay? जहाँ पे classical use कर सकते हैं वहाँ पे classical use करेंगे, जहाँ पे quantum use कर सकते हैं वहाँ पे quantum use करेंगे. Okay? Am I making sense? Okay. So the second table I have given circuit theory and field theory entirely. We have discussed more on that. I have given the physical layer in more detail with some more equations, okay, and finally I have kept a table, argument table, debate question, why this matter for quantum computing, 3.3, okay, which says, is reality deterministic? Page number 6, right, page number 6. Is reality deterministic? Yes, during unitary evolution, it is not always deterministic. Only when you are trying to measure it and it is evolving into one of the outcome, it is deterministic. मतलब इससे हमको क्या मालूम होता है? No matter how much quantum you do, finally the answer should be classical. Answer should be classical. The second is the outcome probabilistic? Do you have a probability? Yes, we use probability only at the measurement. Other than that, it is structured possibility. Idun the Barkoli, please write down. Quantum is about structured possibility. And if you understand this, you will understand all the games of God. Probability is different, structured possibilities are different. So quantum works in structured possibilities. But at the measurement, we have to come to a space where we have to have probability. Okay? Possibility. For example, a coin, as I said, coin is flipped and you have heads or tails 50%, 50%. Whether the coin will come back, if it is beyond gravity, if it is microgravity, if it collapses, if the coin disappears on itself, they are all non-deterministic. There is structured possibility that it may come, it may not come. If you want to explore that, it looks like very vague, but if you want to explore that possibility, you have to work on quantum. It's a structured possibility. It is not about probability. Probability 50% heads, 50% tails, but you never take care of whether the coin will come back or not. So quantum will take care of structured possibilities of all the things. That's why the entropy is always increasing in universe. Everything is structured possibility, not only probability. Probability where I want to collapse it, okay? I am not so able to convince the terminology of that, but possibility, when you observe, measure, it will become probability. Possibility, when you may observe and measure, it will become probability. At measurement, you will have a space, any space, Hilbert says space, you have to have probability. Structured possibilities is, it can go in any way, even you can think like multiverse also. It's a metaphysics word, but we don't have mathematical proof for that. Is uncertainty fundamental? Yes, and we can exploit the uncertainty. This is one of the uncertainty. Okay, and is separability real? No. There is nothing which happens independent in the universe. If you are doing good today, it is good. There will be some balance, there will be some equilibrium in the universe. Everything is entangled. Everything is entangled. You cannot say that only it is a positive sum game. Nahi. It is always a zero sum game. If plus is increasing, minus has to increase to maintain the equilibrium. That is how they are entangled. Then who was right? Whether it was Niels Bohr, whether it was Einstein, whether it was Heisenberg, or whether it was Richard Feynman. All three, but at the context. Okay, so that also argument I have given, classical computing table I think I have given, right? Niels Bohr. Yes. Yeah. On page number 4, I have given their arguments. Einstein, Bohr, Heisenberg, these are the things. Okay, these notes you can use to confuse your colleagues who have not attended the FDP. Okay, you can show off like, hey, I know Niels Bohr. So you can confuse them, but let them later you can conclude that yes, everybody is correct, but at the context, at the measurement, theory of relativity is true because I am measuring at the local, but actually it is non-local. Actually quantum is non-local. Matlab, today you create 2 quantum bits, here you entangle them, and once they are entangled, you ship the one more atom to Japan and you twist the bit here, that will also get twisted. You change the spin, that will also get changed. You change the amplitude here, that will also get changed. They are entangled, so it is not local. Okay? Theory of relativity says locality. The complete movement of any object is related to its vicinity. Like this chair, apply force newtons, there will be a displacement. It can be displaced by another element, but it should be entangled.
So entanglement is a natural process?
Very much fundamental. It is a fundamental process. That's why let me tell you, everything in universe exists in duality other than God particle. Everything exists in duality, and if we explore that, started with the dipole antenna. It made all antennas so energy efficient when we started with dipole antenna. If you explore duality, the best way to understand universe and also get best out of the universe.
So that's why you made a statement that the physics will reveal the solution.
Physics will reveal the solution.
Because we can't make a, temporarily we can't entangle the photon kind of.
If we can. If we can. If we can. See, the engineering definition is manipulation. You see a phenomena in nature, it is science. And it is a theory. You prove it with mathematics, it becomes science. Now, if there is a potential difference, current flows, that is science. I am a manipulator. I will manipulate the voltages to get different currents. So in nature, yes, they are entangled, but by manipulation still can I get more entanglements for my purpose. Electrons flow somewhere, but does it flow in my laptop? So engineer is a manipulator who use the natural phenomena for civilization, for providing a lifestyle. So whatever is available in nature, first let us accept that, and once we know, let us create that in our lab and let us use it put for commercial use. So after that table, I have given classical versus quantum computing stack. तो आपको क्लासिकल में क्या समझ में आया है, क्वांटम में उसको कहाँ पे ढूंढना है. Okay, so the table number 7, page 7, table 4. So whatever you have in classical, madam, did you get notes? Hurry, you have some more, right? 30 ಕೊಟ್ಟಿದ್ದು ಎಕ್ಸ್ಟ್ರಾ ಏನೇ ಇದೆ. ಥ್ಯಾಂಕ್ ಯು. So here if you see, this is a very good treat for computer science people. अब तक अगर आपको लगा ये सर भी electronics वाला है, he is talking only in electronics. This is for computer science. Applications में in classical web applications, databases, CAD, CAM design, AI, finance, ERP systems. Then in quantum you have to go for chemistry and material simulation, optimization problems, cryptic analysis, and quantum machine learning experiments. So these are the things what you have to learn in quantum if you want to migrate from classical domain to quantum domain, if you are a computer science person. And if you are working on algorithms, such as sorting, searching, machine learning, optimization, cryptography, RSA, You have to go to Shor's algorithm, you have to go to Grover's algorithm, VQE, AQ, OA, quantum simulation, quantum kernels, quantum angle of arrival, QAOA, angle of arrival, because angle of arrival has an information, and information is wealth. We are not giving information on electrons, we are taking the information based on the setting of the electrons. So you have you can store more on a single electron. In the phase you can save, in the amplitude of the wave function you can save, and you can save on the spin. So 3 level of information you can save. Previously, electron is flowing 1, electron is not flowing 0. Now you can save more on the electron itself. Electron is a resource person now. So, programming, modeling stack, then languages. If you are learning with high level languages, here you have to go for Open QASM, simulators and all, Quill, quantum circuit representations. If you are working on runtime OS, Linux, Windows, then you have to work on hybrid runtime with classical host orchestration. Okay? And then control layers, processing, IO layers, then hardware environment and physical layer. So this is a stack where if you are in classical in computer science, where you have to migrate. It's a direction for you to search for your problem statements or a domain of research, inquiry. In classical computing, information flows downward as deterministic logic, whereas in quantum computing, information emerges upward from physical quantum processes through measurement. Okay? And then, yeah.
Classical versus the quantum computing stack,
Which is right now in the market. It can evolve tomorrow also.
Sir, the thing is, yesterday also I've been asking the resource position. Yesterday also at home also is just working on some of the mathematical concepts. As we know that we have got some methodology with respect to the logic gates for simplification of the Boolean expression. We have K-mapping, the QM methods are available for us to simplify the
I'll just highlight on that. Thanks for reminding that. So in quantum domain, we are here.
Yes.
In quantum domain, we are here in the logic gates, logic circuits, what you saw in last 4 days. अभी हम यहाँ पे जाना है, हमको यहाँ पे जाना है, यहाँ पे जाना है. Then we have to have general purpose quantum computers. In future, it may take 20-30 years. Okay. Yeah, go on, sir.
So we are having some gates are available with the logic gates, and we are able to simulate some of the results we are able to generate. Few. Very few. Yes, by using combination gates, we are getting some of the results. Now suppose we have some of the combinational equations we have. How can we see polynomial equations? Because when I day before yesterday and yesterday when I explored with the simple quadratic equation, it gave me 500 line code.
It fails.
It's give me and there is no proper methodology being defined for solving a quadratic equation.
Okay.
So how can we employ our classical knowledge of solving the polynomial or SOP or POS form to the quantum circuits?
I would say technology has to evolve to that level where I have stable quantum bits and quantum bit remain quantum bit for more than at least 9 seconds. Here within nanoseconds it is losing out the photon and it is becoming a normal electron without any information. So once I have that much of time, a delay when you have a buffer, then only you can operate. What you are saying, the combinational logic, it works only when you have a latch. Latch matlab 1 bit buffer. That is still not possible in quantum. So we are at the gates. We are not at the combinatorial electronics where you have polynomials. So hard NP problem mein P means polynomial, still we cannot solve polynomial. But that's what I said. We are at gates, we are not here. So your search is good. You have to do inductive research. You have to come up with something out. Yeah. Yes, yes.
What we develop in VLSI, ultra ULSI, then we have to develop a circuit which can able to work at qubits.
The VLSI circuits, they store for 30 years. They will flush on their own when the power is removed. But qubits, no matter you maintain all that minus 273.4 degrees Celsius, within 9 seconds they will lose their quantum behavior. That's why we are not able to go beyond logic gates as of now, limited by technology, but we are in this era of that.
And they are not, some more research I was just doing on that. There no clear methodology has been defined for converting a classical equation into a quantum equation. There is no method.
No. That's what I said. Madam asked the very right question. If you say structured possibilities, can you extrapolate on that? Can you explain more on that? Probability, I can derive all the equations. Structured possibility, I have to define the structure of the universe first. So there is no mathematics for that still now. We have to go, like we have to explore Srinivasa Ramanujan's last 36 equations which he wrote on his deathbed. Only 8 have been understood now. So remaining equations have to be understood. Such new mathematics has to be developed. Like we developed calculus for 3 dimension. When we entered field theory, we developed calculus. And when we went for possibilities in the probability, then we developed linear algebra. Right? Linear algebra we never respected until we cleared the aptitude rounds. And when we came for AI, especially AI, linear algebra, all mathematics department got huge scope. Anybody who was knowing linear algebra, Andrew Ng, the famous most watched Coursera course is linear algebra for AI, machine learning. So we have to develop a new mathematics. We have to. We are at the mercy of mathematics to understand more quantum.
So for structured possibilities, as you mentioned, if I'm not wrong, in my understanding I have observed like, input is like flipping the coin.
Yes.
Output is getting head or tail.
Tail.
And in between there is a flip where
Trajectory,
this thing, can we define that one as a structure? So
Now if you define it will become local.
no, that's also deterministic could be there. No, sir. Sometimes if we try to stop in between and try to find out the possibility, and the structural possibility is the path.
No, you have just reduced the time. You will see the coin flipping here. If you hold it in between, then you have reduced time. You are still in the 2-dimension localized axis.
So possibility is like
It has to be.
how much time it is taking, it comes in the classical.
Yes. We have to have new notations and mathematics for that. Just like circuit theory has quadratic equations, combinatorial electronics. But when it comes to field theory, reflection, total internal reflection, do you say reflection of current or voltage? So every domain needs its own mathematics. नहीं तो mathematics syllabus saturate हो जाता था. So the mathematics of waves is reflection, total internal reflection, propagation loss, path loss, AWG, additive white Gaussian noise. So that mathematics is completely different from your logic design. And it is completely different from your Sambhavaniyate, probability. Right? So we have to have new kind of approach and mathematics very much required for that. Then we have, table 5. This is very interesting. This is where things should get into more engineering. थोड़ा अच्छा डस्टर है क्या मैडम? Okay, I'll explain to you here. I think I have a backup also. Yeah, next page. Go to the next page. Page 10. Now here, at the center of the matrix, this is a matrix, okay? This is a matrix what I have created. At the center, you write any technology. For example, now it is classical computing. We will take classical computing, all right? This is a matrix which helps you to innovate and to get new possibilities in engineering, okay? At the center, it is classical computing. For that, how it was done earlier. Here I have written, pura, all, entirely. Is it possible? Yeah, good. I'll use black then. So here it is classical, modern classical engineering, okay, computing. Before that, it was just a classical computing. Okay, classical computing यहाँ पे है, which was based on vacuum tubes, diodes, BJTs, MOSFETs. Then we have classical computing where we have VLSI. Okay, and the next will be quantum computing. This is a simple matrix where I have helped my students to write or design patents within 20-25 minutes. Okay, from this you can get patents on quantum by this matrix. Whatever is there in classical, modern classical engineering, you should write it here. And usse pehle jo tha, the precursor, you should understand. How do you do that? You take the patent of that. A simple example, smartwatch. Here it will be smartwatch. Before that it will be a digital watch. Digital watch, smartwatch, next will be quantum watch. Right? So normal digital watch, this is a smartwatch with sensors, and this will be quantum watch. Okay? Anything. If you want to have a patent in 20 minutes, this is the easiest matrix. Now, the first wala, जो भी old method है, the traditional legacy system, you write limitations of that. And you don't write limitations on your own. Again, you find the patent of digital watch. Take a patent of digital watch, and they will have some limitations. After the claim, they will say it doesn't cover this, it doesn't cover that. So those things should come here. The limitations of this system will be application of the next level. So here in digital watch, the limitation is you cannot measure health parameters. Okay, the limitation of old legacy digital watch is you cannot measure heart rate. You cannot measure number of steps. You cannot give blood pressure, any of the readings. The next smartwatch will have sensors. It will be embedded with sensors. It will have these things. It will have healthcare applications. It will give you your vitals. It will give all the readings of your biological details here. Okay? But once you have that, what more do you need from your watch? What more do you need from your watch? If you can visualize that, if you can guess that, if you ask that to your parents or anybody, and if they give some vague thing, write that as a limitation, and that should be claimed in your patent. This is your patent. Simple, na? So this patent document is available, this patent document is available, this is under your name in 6 months. So start applying for patents on quantum domain. One guy simply registered his web as google.com, and within 18 hours Google purchased that domain with 70 millions because they want to have that domain. They cannot afford to have somebody else with a google.com. The moment they announced the company name, this guy sitting in home, he registered his company google.com. He got 70 millions just by registering a company free of cost on website. So aap kya karo, being teachers, have 4 to 5 patents on quantum. Communication algorithm, quantum communication algorithm. Channel capacity, quantum channel capacity. Machine learning healthcare, quantum machine learning healthcare. See, everything has to be faked before it becomes real. My kids, they fake that they walk and then they started walking. They never waited up to 4 years and suddenly one day, today I am ready, I got the OTP from God, I will walk. Aisa to nahi hua. You have to fake it until you make it. So first have patents on quantum. That will give you confidence. And this is the only page and matrix which will help you to get easily, okay, thought process. Simple things. You take anything, microphone, quantum microphone. Can you give me, give the health vitals through my voice? Can you, through my sputum, can you tell whether am I going to get cancer after 11 years or after 7 years? That is very much required. Early detection is very much important. We are going for that in next 1 hour. We will discuss more. Yeah, समझ में आएगा? Everybody is on the same page? अर्थमाइंदा? Okay. So center में जो existing है, that patent, which they have referred, that patent, and which you are going to write, that patent, their limitations will become your claims. So, if we go on that side, okay, you want the legal things or technical things? Okay, suppose there is an innovation, I want to claim, a simple example, there is a jug with one handle. Jug with one handle. Yeah. So there is a jug with one handle. It is already existing. I will make jug with two handles. Now, will it be patented or not? Yes. It should have usefulness. Where it is useful? एक हैंडल से जग संभाल रहा था, तो क्यों दो हैंडल का जग बनाया? Kids can use to handle one thing, and ceramic and porcelain things will break with only one handle because the strength of material will go on that side, so you give on both. So idea plus claim. Technical nahi hai. Claims. How much it is useful, you have to claim. And if you can give a diagram for that, it becomes a design. If you can prove it in real time, it becomes utility. But for in real time, you have to face the examination. In design, the examiners will validate, yes, it is unique. So logo design is also patent, and there are many patents like geotag. Gulbarga Tur Dal is geotagged. Tirupati Tirumala Prasadam is geotagged. Geographically tagged. Indicator. So patent is something which is unique, which you want to make it as an intellectual property. So that is patent. In that you have design, utility for engineering purposes. All remaining are for various things. Unfortunately, we cannot patent business idea. That's why we will have FDP, we will give all the ideas here. Okay, so business idea cannot be patented. So uske liye aapko kya karna hai? You have to make a computer, a transmitter, a receiver, and you have to tell the business idea between those two systems, and you have to patent it. Okay, suppose you want to patent LMS. Then you have to say transmitting system, master slave system, you have to make them unique diagrams, 101, 201, 301, you have to make diagrams. Then the business idea should be the claim of that. Then it will become a patent. Think that would be sufficient for now. So you will need to have an attorney who will help you to face the examination, or who will face the examination on your behalf. Design patent is very simple. Utility patent, only 1 out of 2 lakh applications is approved at a ratio. 4.
It will take some years.
To 18 months for first examination, 6 months for re-examination, and for grant of patent within 3 months. So it will take 2 years, 8 months to 3 years. If they want re-exam, it will take 4 years. And if it is DRDO based, it will never be sanctioned. So, yeah. Unique characteristics of quantum, I have given characteristics, 10 characteristics, which I have explained there. Then we are moving to, what is the time now? How much is it? 10:35. This is very important zone. This is where I feel I will touch many people's requirement. Migrating from classical ML to quantum machine learning. Okay, so page number 13, evolution from classical machine learning to quantum machine learning. Okay, now you understood the matrix. I have filled the matrix for machine learning. Page number 14, I have filled for classical computing. I have done it for classical computing. Okay, and then on page 15 I have done for ML and QML. I have filled the matrix, the patent matrix, what I have developed. With my knowledge, I have filled it here. So here you will come to know in machine learning what all things are expected, what things should be written in the claims, and how it has to be done. So I gave you a small glance of patent, how to have patent in quantum domain. Okay. So
when you are going with the CMOS technology, so is there any loss of it? Because we have got lambda-based design tools are available for designing simple AND gate or gate. We have got, and we are using the what color coding of identification? Has it been done with the quantum?
No. Even lambda based, we are exploring quantum. It is not about research. It is our basic need. Why? Because VLSI has 2 million transistors on a single wafer. And your new transistor cannot be smaller than an atom. So we have reached the limit of Moore's, where it says W by L, the lambda ratio can be reduced every 2 years. Now we cannot keep on reducing for next 7 or 8 years, because if we go on reducing, it will be less than an atom. Can transistor be less than an atom? Highly impossible. We cannot have a gate, we cannot have channel, we cannot have flow, we cannot have voltage difference. Because when we get into atom, it is not electric force. It is nuclear force inside the atom. That's why the electron is negative, proton, the nucleus is positive. Why are they not getting attracted?
Opposite also force.
Opposite. They should attract. Why are they not attracting?
Because of the speed.
Because there is another fundamental force called as nuclear force, which keeps them away, so that one becomes center, another will rotate or revolve around that. There we come across centripetal and centrifugal forces. So electric force is not applicable within atom. That's why our VLSI stops here. In another 3 years, the saturation is there. Below 9 nanometer, we cannot go beyond that.
So then what we have in the classical methodology of CMOS technology, then we can't implement in the quantum.
No way.
So again we are
That's what, sir.
classical.
That is why I said circuit theory is completely different, field theory is completely different. This mathematics cannot be done here. यहाँ पे आप antenna design कर सकते हो, यहाँ पे आप gate design कर सकते हो. With the gate knowledge, you cannot come to antenna. No way. In the same way, with the antenna knowledge, you cannot go to quantum. Okay? So that is how the progression is. This is QML. Shall we break? Yeah. In 2 minutes, madam, we will break. इसके बाद में full लिखने का है यहाँ. Okay? So this is the matrix what I have created. I have added 2 more rows for your benefit. One is applications, problem lengths, and one more is applications. This will help you to understand any domain very easily. Okay? So you have the 3x3 matrix above, and then you have 2 more rows. One is problem lengths, what problems are entertained in that domain, and then you have application row, what applications are achieved in that domain. Okay? So this is about QML.
Sir, can we design quantum antenna?
Can we?
Design quantum.
Let us first patent it, then we will. Normal antenna, dipole antenna, नहीं तो your normal antenna, fractal antennas, quantum antennas. सबका नाम लिखो, everybody is innovator. You first file the patent, then we will work on that. Quantum antennas are required. I have all the papers, whatever you are asking. See, these are the papers what I have referred for to talk the entire session. So everything has a proof. Quantum antenna, there is a paper. And even how to introduce quantum as a UG program, I have 3 papers here. Okay? And how to become entrepreneur, innovator in quantum domain, 1 paper is there. Okay, 43 papers are there. I have referred all those things. अभी ये क्या बोलते हैं trailer before the break, don't go anywhere. Break नंतरा. See here. If you have a problem statement, my next 1 hour session or 1.5 hour session is going to be very, very beneficial, where I will take your complete PhD, title, objective, hypothesis from normal machine learning space to quantum machine learning. Okay? We will change the title, we will change the objectives, we will see where it is required, where it will be changed. I will also highlight what part of the journal papers have to be changed when you go from this domain to that domain. Okay? Kahin na jana jana. Let's break for 5 minutes.
Back.
Okay, sit straight. Take a deep breath from your nose. Exhale from your mouth. We'll do it again. Inhale. Exhale. Once again. Inhale. Stop. Okay. Every time when you define a PhD, you start from this plane. Okay? Independent. You start a PhD from independent variables and you go towards dependent variable. Okay? My topic is research, so I am explaining in this way. You start with independent variable, you go towards dependent variable. Now, what is independent variable? For example, text data, it is independent variable. Image, it is independent. Okay? Any data, it is independent. But from that data, I want to detect something. I want to make a decision. So that is a dependent variable. So detection, classification, decision, these are dependent. The decision is dependent on data. Data is not dependent on decision. नहीं तो match fixing हो जाएगा. Okay? Based on your decision, if you start collecting data, then it is match fixing. Okay? It's a malpractice in research. So you have independent variable and you have dependent variable. The way you relate your independent variable to dependent variable is hypothesis. The way you relate your independent variable to dependent variable is the hypothesis what you try to make out from your PhD work. Okay? Now, going one step beyond, with the text data, the attributes height, weight, previous medical history, with all those data, I want to detect cancer. That clinical people will also do. Medical people will also do. What you are doing, what doctors cannot see, your machines will see. Your algorithm will see. Your data will show. That is why we come into cancer detection. That is why we come into medical diagnosis. That is why we come into healthcare. So अगर आप MBBS करना चाहते थे और डॉक्टर आपके नाम के पास रहना चाहता था तो PhD कर लो, डॉक्टर आ जाएगा और get into healthcare research, you will be working with doctors. Okay? And preferably in a university where medical college is also there, engineering college is there, you will get the data from medical college, you publish here. I have entire, next 1 hour is only one scenario we are discussing. Machine learning for cancer. So we are writing hypothesis now. Next, ade barita ide. Yes. Okay? So, ಈಗ ಹೇಳ್ತೀನಿ ನೋಡಿ. Text data is independent. Early detection is dependent. Detection is dependent on text data. Hypothesis 1. Using machine learning for early detection of cancer, tumor, anything. This is hypothesis 1. Hypothesis 1 says that I want to implement machine learning algorithms and optimize them such that early detection happens with the text data, attribute data, height, weight, smoking history, exposure to pollution. All this textual data, I will use it and I will take a decision whether there is a cancer or not. Hypothesis 1. Okay? With that, have you detected or not? That becomes hypothesis 1. Okay? Second hypothesis. Now, detect हो गया. अभी cancer detect हो गया. Next क्या करेंगे? How much it has spread? Okay? So, diagnosis. And how do you do that? You do it with image. Text will not tell you now. The age will not tell you how much it has spread. The pollution will not, exposure to pollution will not tell you how much it has spread. So now you need the images, the malignant, benign, those images are required to tell, it is in stage 1, it is in stage 2, or it has been spread to lungs, it has spread to chest, it has spread to the bone. So that is only possible with images. And that doctors will also do. What you will do? You will do accurate diagnosis using ML. Sir, second hypothesis. Machine learning algorithms or using deep learning algorithms for image data for hypothesis 2. Done. Hypothesis 3. Once the cancer has been detected and once it has been diagnosed, whether in stage 1, stage 2, the doctors start giving treatment. You will start taking the various solutions of that, including chemo and all. Now, how much the medicine was impactful, how much the disease has been controlled, how much it has been solved, that will be given in prognosis. 3 महीने के बाद में prognosis result क्या आया, 6 महीने के बाद में prognosis result क्या आया. After 3 months you don't go again for detection. Already it is detected and it has been diagnosed. Now how much your medicine is impacting, what is the fruit of all the medicine, so that prognosis. Okay, so that will be done by biomarkers. And here that doctors can also do, but it should be precision. अगर lung के पास है तो वहां का precise you have to target that cell. अगर esophagus का है you have to target those cells, like that. So it should be precise. So these red words make it engineering problem. All the black make it clinical problem. It's a medical research and only the red terminologies will make it engineering. Okay? If you are just detecting, we don't want it. Doctors will do. If you are detecting it much early, before the doctors will detect, then we need such solution. We badly need that. Diagnosis, doctor will do. Can you do accurate diagnosis? 17 days passed from stage 1 and 3 days just behind stage 2, already in stage 4. That accurate. Cancer ide, spread agide, naaleanta banni, chemo madona, nodona. This is how doctors work. But your machine learning algorithm, if I give the data, if I give the images, if I give the biomarkers, can you tell me accurately, diagnose it accurately? And once I start taking treatment, can you precisely prognosis? Like you are targeting the kidney, but it is hitting the liver. It should not be in that way. Okay? So all the red words make it engineering problem. Samajh mein aa gaya? So now next 1 hour for this, I will just add okay. So after listening everything, after finding the basics, logic gates and seeing the photonics in CDAC, when you go back to your college, it will be just old traditional system. The laptop will be classical system. यहाँ जो भी जोश आया है, वो 2 दिन में you will be frustrated. That's why I am bringing you back to the lab and I am helping you to do quantum research without getting frustrated. So next 1 hour is very, very important. We are going to discuss many things. We have to write many things. Okay. Now we have written this. So this is how you create a problem statement and this is how you create a hypothesis.
We are dealing with cancer.
Yes.
And there are very different types of cancer.
400.
But how we are going to go for the diagnosis with respect to the blood test, because
only 40 cancers are detectable and they can be serviced. Other, you have to be at the mercy of that. Out of 400 cancers, only 40 can be detected and it can be solved. वो पूरा इंजीनियरिंग टर्म में सर्विस कर सकते हैं. It can be solved or it can be taken care. Other than that, nothing.
Breast cancer we can't solve. There is no solution.
No, because it goes into bone marrow. Production is faulty, then none. That's why there are India is going to be cancer capital by 2040. Every 1 person out of 5 will have cancer. If you are investing anywhere, invest in cancer hospital. But first invest on yourself that you should not have cancer. नहीं तो जो भी आया पैसा वो फिर आप वही hospital को डालोगे. But that is the truth. That is a fact. Okay, Punjab is already suffering from that. Okay, so are we clear with this? This is how title, problem statement, the entire landscape will be defined. Okay, so from here I will go with this, but adding all the details. Finally, we will have KML. Now the hypothesis will be like exploring quantum to detect for early detection of tumor, brain tumor, cancer or anything. That will be the hypothesis when we come with that. Artha aita na? Idu gottaita? Please, go on, please.
Instead of detection, pre-curing.
Then precaution. If you take precaution, you no need to come to hospital. That can be a byproduct. Like if it is not detect yes or no. If cancer is no, then you give what all things you should do so that it will never be yes. Yes.
That itself is a problem statement. Because of the business.
Which one?
This detection.
No, not business. People are suffering. That's why it is business. If we all stop using cell phone one day, Meta will fall, Google will fall, everybody's share will fall. Since we are consuming it continuously and since we are having cancer continuously because we take PPP, processed, preserved, packed. Until we have these three, they will be there. But unfortunately, there are people who are succumbing to cancer who never were part of the metropolitan city. Even the people who work in fields, they are having cancer. We don't know. So as I said, it's a structured possibility. So shall I go ahead? Oh, this duster is very nice. Yeah. Now, construct A. You have new page, next page, please. Done? Okay. Let us be fast. Next is construct A, construct B. Then we have independent variable and dependent variable. Full landscape mein likho. Let us write in this way. Itara pariyona, okay? We will write in this way. This is nowhere on internet. Huh? One and only yahan pe. Okay, construct A, construct B, independent variable, dependent variable, they come here. This becomes proposition and this becomes hypothesis. And in the previous page, what we saw, hypothesis 1, hypothesis 2, hypothesis 3 will be your objective 1, objective 2, objective 3 of your papers. Here it is proposition and this is hypothesis. Okay, this is called as theoretical plane. This is called as theoretical plane, and the below it is called as empirical plane. The above is called as theoretical plane, the below is called as empirical plane. Now, here, what you assume, comma, what you assume, model, what you assume, comma, model, comma, and formalize, Okay? What you train here, what you train, measure, what you train, measure, and evaluate. What you train, measure, and evaluate. Okay? Here, constructs learning assumptions. Constructs, comma, learning assumptions. Constructs, comma, learning assumptions. Here, data set, variable, parameter. नीचे, data set, variable, parameter, metrics, experiment, metrics, experiment. Done? Now, with the example of cancer detection, construct A is nothing but multimodal clinical evidence. This is multimodal clinical evidence. Multimodal clinical evidence. This is cancer state understanding. Here I am taking example of cancer. You can do it for network also. Networking, channel capacity, whatever it is. From ML, I am migrating to QML. You can do for QC to MC to QC. Okay? Some machine computing to quantum computing. So, multimodal clinical evidence. The proposition is, I will get an understanding of the cancer state. How do you do that? You come here. I use independent variables. What are those? Text, image, data, sputum, text, image, data, sputum, DNA signature, biomarker. Okay? Either side. Here, cancer detection, cancer spread, cancer detection, cancer spread, then prognosis outcome. Then prognosis outcome. Done? This is feature space. This is feature space, and this will be model, and this is what you will be doing to create a machine learning model to detect early. So this is the model. This is feature space, and this is model. So this is feature space and this is model. This is data and this is prediction. This is data and that is prediction. Okay. Here data is represented as vectors and tensors. Here data is represented as vectors and tensors. Data is represented as vectors and tensors. Okay. Here we will have learned function and decision boundary. The threshold, if it is more than 35%, then yes. If it is less than 35%, then no. So such kind of thing. Learned function, matlab wo train ho gaya model, and you will take a decision on that. Decision boundary. Okay, so this is the entire landscape of your objective hypothesis, and if you understand what falls where, then you can easily answer any examiner and you will be in the right direction of your research. Nahi to, every time you will romance with every new term of your domain, and every new paper will demotivate you that it has already been done. Okay, until you don't have this clarity. If you have this clarity, then you can explain what is unique, what is different, what you have done a separate way, in a different way. Okay, so this is the entire landscape, and this landscape I will call it as machine learning. So machine learning में cancer detection, data क्या है, construct क्या है, theoretical plane क्या है, empirical plane क्या है, बता देता हूँ. Did you ever get a question that in BTech faculty ask show me the output, in MTech they will say show me the simulation, but in PhD they will never ask? Because they will be questioning here. They will never question here. And if you are unable to answer this, they will ask what is your data, what is your selection, what is your split ratio, what are your parameters, what are your hyperparameters, what are your outcomes, what is your region of convergence, what is your sensitivity, what is your accuracy. But if you explain here very clearly to them, they will never come here. If you say, my proposition is, I want to understand the state of the cancer, whether it is there, if it is there, how much it has been there, since how much time, and if it has been treated, how much the medicine is affecting. I want to understand that through my clinical evidences, where I will collect the data and I will use artificial intelligence. Okay, so this gives you AI in healthcare. This gives you your thesis. So whenever you do PhD here, when you take data, when you take image data, when you write the machine learning algorithms, when you bootstrap them, when you optimize the algorithms, and you detect the cancer, when they call you as a resource person, you don't explain this. You explain this. And if you cannot bifurcate between these two, then examiner will play with the questions. They will ask one question here, they will ask one question here, they will ask one question here, they will ask one question here. So you should have the bifurcation of this theoretical plane and empirical plane. And this will help you to migrate to any point. Now I will take you to quantum with the same diagram. And I will tell you what changes, what doesn't. Okay? We have some idea here. Turn the page, write 5 important points. Core assumption, the core assumption. Turn the page, write 5 important points. Core assumption, patterns are learnable. The core assumption is patterns are learnable Patterns are learnable via optimization. Is your machine learning? Yes. How much you are optimizing? Others' machine learning is also learning. How much you have optimized? How much less resources you have used? Then your paper is unique. Okay. Second assumption, maths. In maths, second point, maths. You will use linear algebra. You will use probability. You will use linear algebra, comma, probability, and calculus. Okay. Next point, learning view. So what is your focus in learning? Okay, learning view. Learning view, colon, optimization over the parameter space. Optimization over the parameter space. जो आपका पैरामीटर का जो भी लेआउट है, okay, accuracy is a parameter, efficiency is a parameter. Are you optimizing? मतलब somebody has achieved 80% efficiency. Are you able to achieve 90% efficiency? If you are achieving 78%, then your research is not appreciated, not required. When somebody can achieve 80%, why your research is required? Then if there is a fundamental difference, you have to justify. But the question is like that. Last, correlation model. Correlation model. Mostly local / pairwise. Correlation model. Mostly local / pairwise. Matlab, what you will do, you will put the results in pairwise, right? Efficiency, epochs. Then accuracy, epochs. Number of training epochs and all. This is parameter, this is hyperparameter. Hyperparameter is something which you set before the experiment. Parameter is something which keeps on changing during the experiment. Efficiency keeps on changing. Hyperparameter, only 30 per epoch. Training set. Split ratio, 30-40 training, 60-40 training, 70-30, like those ratios. They are all hyperparameters. So you will show the result in this way. Pairwise you will show. For 30 epochs, this is the efficiency. For 60, for 90. Then with GPU, with CPU, with CUDA architecture, with accelerator. So pairwise you will show the results. This is how machine learning works. Last point, challenges. Last point in that, challenges. Challenges. Noise handling, bracket, statistical noise. Noise handling. Here it is not an analog system to have channel noise. So you have to handle statistical noise, like data missing, data repetition. So you have to handle those noise. Then comma, not comma. Next line, experimental loop. Next line, experimental loop. So how do you do experiment? You train, you validate. You train, you validate. So train, arrow, validate. That is the loop. You train, you validate. You train, you validate, right? Then scalability limits. Third point, scalability limits. So these are the three challenges. Scalability limits mein data size. Data size is the biggest issue with all the ML researchers. They are at the mercy of all the websites who provide the data. They cannot go to hospital and get the clinical data. So scalability limit is data size. Kitna acha data milega aapko? Like my students do cancer detection with the data of Brazil. So that data is different, Indian data is different. Even if you come, South Asian data is completely different. Okay, so until you come below Bangladesh, your data is not correlating. That is a statistical problem. So these are the things what you have in machine learning. Are we clear with this? So now, same problem we will migrate to QML, quantum machine learning. Go to the next page. Construct A, construct B, independent, dependent, proposition, hypothesis. Everything which is in black, please repeat it. If you want papers, please. Is it making sense?
Yes.
Yes. Oh, इतना डूब गए वो बोलने को भी. This is a flow I created yesterday night. Like somebody said, there are some few PhD people also who have come for FDP. So I completely changed it. Construct A, construct B, theoretical plane, independent variable, dependent variable, empirical plane. Empirical plane is where you work. Theoretical plane is what you explain. What we understand also. Because with PhD you are just pushing the circumference. But the complete circle will be in theoretical plane. And this bifurcation will help you to understand how to migrate. Sumaya madam, correct time ko aa gaye tum. Hypothesis. No, that's the right time for it. Done? Okay. Here what we had written, data represented as vectors and tensors. Now data encoded as quantum states. This please. Data encoded as quantum states. This side, we have written learned function. Matlab, when you train the model, it becomes a learned function, and this trained model you can use it for brain tumor also, lung cancer also, any type of cancer. The model is ready. That is machine learning. Now it is quantum evolution plus measurement. Quantum evolution plus measurement. So quantum will be evolving and you will measure to know the outcome. Without measurement, it is superposition only. Riyaz sir is teaching good, Riyaz sir teaching is bad. He is efficient, he is inefficient. Superposition. Until you stand and observe, today's session was efficient, but other things are inefficient. I see. Okay. So data encoded as quantum states on this side, quantum evolution plus measurement on this side. Here, quantum encoded states. And this side, it will be measured outcomes. So this remains same. Previously it was prediction. Now also it is prediction. That is measured outcomes. Okay. So इससे हमको क्या पता चलता है? Empirical plane will not change much. Your data will remain data. Your protocol of validation will remain same protocol of validation. Your parameters will remain same parameters. Your hypothesis will remain same with only one additional term called as Q. Okay? But there is a major change at theoretical plane. Here, the complete states are encoded into quantum, and there is an evolution of quantum and measurement of quantum. So those things, यहाँ पे आपका data same text रहेगा, image रहेगा, video रहेगा, and outcome will be detected, diagnosed, prognosis same, it will be there. So यहीं पे देखो, see how different it is. People will just add another term in the title for machine learning, call it as quantum machine learning, and do the same, but they become quantum resource people, and that is the right way. Because the evolution what has happened in quantum till now, we can only use this much. So if you are becoming a ML engineer in 2 years or 3 years, if you are getting a PhD in AI, better get it in QAI. And if you are getting a patent, smartwatch, AI watch, quantum watch. Okay, so these are the parameters. Next, turn the page. Before that, here quantum state encoding, more detail. Quantum state encoding. Quantum evolution for plus interference. Quantum evolution plus interference. I am giving more detail to you so that you can answer to the examiner when it comes for your Viva. State preparation. Same, it is again measured outcomes only. State preparation. Done? So आपको क्या करना है? In machine learning, you will take the data, do the data cleansing. Now in quantum, this data should be imposed on quantum states and let them start behaving as qubits. Here you measure them and say whether the cancer has been detected or not. We are not going to change the entire craft of this. So this is the Q domain, okay? This will become QML. Write the heading QML. Turn the page, we will write 5 assumptions and 3 challenges.
When we are classical, we are having text data, we are having public.
Yes.
But still, the quantum is just evolved. How can we focus on the
This is a structure for next 10 years of evolution. After this, I will give you what is mapped to what also. After this page, I will give you what is mapped, what is retained, what is completely changed, what is redefined, what is just reworked. वो भी देता हूँ. Turn the page. 5 important points. What is the first point? No. The argument is core assumption. Core assumption. Core, not code. Core assumption. Here it is. Structure is revealed via interference. Core assumption is structure is revealed via interference. The core assumption is structure is revealed via interference. Structure is revealed via interference. Okay? I told you in the inauguration, right? My mother used to keep gates and all the waves towards academics, they interfered constructively. Towards industry, they interfered destructively. Even I am a national level football player. Again, destructive overlapping. Only academics. So, second, what is the second argument? Maths. Hilbert spaces. Pallavi madam yaad aa gaye humko. Hilbert spaces, comma, operators. Hilbert spaces, comma, operators, and alpha and beta. What is alpha and beta? Amplitudes and amplitudes. What is the third argument? Learning view. State preparation. State preparation. You prepare the state based on the data and you evolve. State preparation plus evolution. Evolution is not your Darwin's evolution. It is an engineering evolution. The LTE. What does LTE stands for? 4G LTE? Long-term evolution. So, वो evolution dinosaur से human being वो evolution नहीं है. ये evolution है. You give the data, it starts evolving. Now the spin has information, the phase has information, and the wave amplitude has information. That is evolution. Normal state, excited state. So there is evolution. This evolution. Okay. So learning view is first you prepare the state and allow it to evolve. And at one point you interfere and see and measure, and then you will say cancer has been detected or not. Okay. Next argument. Correlation. That was, what was there? Local. This is global. Global, high order, global, high order. In the bracket, what do you call the correlation? This bracket entanglement. So these are the 4 to 5 points. The fifth point is challenges. Challenges में अगर फिर हम 3 point लेंगे, okay? Challenges में. In the challenges, first is noise handling. Noise handling, colon. यहाँ पे क्या क्या noise होते हैं? What was the noise there? Statistical noise. If your data is imperfect, then that adds imperfection. यहाँ पे you have to take care of quantum noise plus statistical noise because you are encoding same data. So quantum noise plus statistical noise. You have to deal with 2 noises. सर दर्द भी और सर्दी भी. When you take a co-guide in your PhD, this happens. There is quantum noise also. There is statistical noise also. Done? उसमें second challenge. What is the second challenge? Experimental loop. वहां पे क्या था? Train, validate था. यहाँ पे prepare, arrow mark, evolve, arrow mark, measure. Prepare, evolve, and measure. Prepare the qubit, evolve the qubit, measure the qubit. Measure the interference. Okay, what is the last one? Scalability limits. Qubit count. वहां पे data is a challenge. यहाँ पे qubit is a challenge. Whenever you say I want to implement, I will say only 4 bits are not more than that. Only 5 bits are not more than that. So that is the biggest scaling bottleneck. We cannot go beyond that. Okay. So qubit count / quantum noise. The more bits, the more noise is there. That's why they invest gold in the chandelier to reduce the noise. Gold is very stable metal in noise. तो अब आपको समझ में आ रहा है how we are migrating. First day what you learned, second day what you learned, third day what you learned, that will fade away once you go back to college. And once you say, Macha, I learned everything, I will do quantum machine learning, then where are the qubits? No qubits. Evaporated, faded away. And they are entangled somewhere in HKBK. I am here. Right? So that's why I thought like we will work in this way where it will help you to migrate from your ML paper. Previously, if you have published a 10 ML paper, in next 3 months you can publish QML paper. You can add me as a co-author also. I'll give the details. Quantum infinity group. Done. Now we will write some 7 important points, and after that I will tell you which section of the paper will change, what parameter is replaced by what parameter, what terminology is replaced by what terminology in the quantum ML paper. Shall we do that? Okay. These are 7 important assumptions. Please make a note of this. तीन देख छोड़ो, उसके बाद में क्वांटम पेपर को भी होना है. पीछे the problem with engineering is we don't have sophisticated labs. That is the biggest challenge. If I spend 5 years in any lab, obviously I can generate some qubits, but where is the lab? शुरू होता ही खत्म हो जाता है. Take 3 pages. Done? Ready? First point. Title is key takeaways. Key takeaways, it is for migration. When you are migrating from ML to QML, these are the 7 things you should know. Key takeaways, the heading is key takeaway. In the bracket, while migrating from ML to QML. Key takeaways in the bracket while migrating from ML to QML. Okay, first point. Empirical plane changes moderately. Empirical plane changes moderately. Empirical plane changes moderately, while theoretical plane changes fundamentally. While theoretical plane changes fundamentally. Artha aita? See, you do same PhD with same data, same decision, detection, prognosis. Only thing is you encode the data on quantum. But when you come to the theory of it, if you are doing machine learning, you start from a linear algebra. But here you will start from Hilbert space. So your entire theoretical landscape will change, your language will change, your notations will change, your mathematics will change. You come with linear algebra and calculus here in machine learning. But when you come to quantum, you come to physics, you come to entanglement, you come to superposition, you come to interface. Illi farak badala. Illi bada farak badtade. So PhD karna आसान है, उसके बारे में theory develop करना बहुत important. That's why BE, Bachelor of ME, BTech, MTech, BA, MA, BSc, MSc. But for all, it is only PhD. That means there should be a change in your philosophy. If your philosophy doesn't change after your PhD, then the PhD was another MTech with 3 publications. How does your philosophy changes? When you talk about the theoretical plane. You say that machine learning has limitation, quantum has future. These are the things in quantum. How do you know that? I understood while I was doing PhD. So you should always talk about this, do this. Talk this, do this. Unfortunately, my scholars get confused among this. They always talk about this, get instructions when they are asked from here. How many quantum bits you have seen? I don't know, sir. Riyaz sir told to make it quantum, I made it quantum. But accuracy is good, sir. Right? You say, I was doing machine learning, then I came across a paper which was quantum. It was not tough. No need of quantum. Just a small gate, a connector, and I have to pass that through Quniverse software tool, and I was getting quantum output. Then I understood quantum has bits. Then they will not ask question. They will say, Namgu salpa notes kodi. Artha aita? So, you do this, you talk this. If you talk about this, you will get stuck. You should talk about this. That's why it is PhD, Doctor of Philosophy. Heisenberg is the only person who got Nobel Prize for his thesis. Okay? Because he spoke about this. I cannot give the position and the speed at a time. If you take the speed, the position is uncertain. If you take the position, the speed is uncertain. 1.5 page. It's a lemma, it's a theorem. And he got PhD for that. And he got Nobel Prize for that. तो इधर बात करो आप, यहाँ पे आप सॉल्व करेंगे PhD, बट यहाँ पे एक इक्वेशन दोगे, E equal to mc square, done. Planck's constant, done. Photon, h nu, done. Black hole, what is his name? Stephen Hawking, he didn't prove black hole, but he gave an equation here. 2.5 pages were blank in his thesis. Proof was not there, theorem was there, lemma was there. He was awarded PhD. And he wrote antithesis for his own thesis and again got PhD. That is the beauty of research. That's why they give philosophy. Doctor of Philosophy, not technology, not engineering, not science, not arts, not humanities, not performing arts. PhD is PhD. Matlab, aap PhD kare ho, you have a different level of understanding. It is just like the people who are busy with small things, small rituals of the religion. But the people who know God, they are beyond religion. They are spiritual. They try to find God in everything. Every work will be a purpose for them. Same way, that is why PhD is mandatory for teachers. With PhD, you get maturity that everything is not absolutely correct. Without PhD, you say, hey, everything is possible with quantum. But with PhD, you say, ಎರಡು ಬಿಟ್ಟು ಸಿಗಲ್ಲ. Right? So without PhD, you understand that everything. So if you go with low people, they will say, doing this is religion. Doing this is religion. But if you go with spiritual people, not believing in God is also believing in God. At least you are thinking of God. Right? So that is how your philosophy has to change. Okay, I am going into philosophy. I have to come back to So empirical plane will not change much, moderately, but theoretical plane will change fundamentally, not drastically, fundamentally. जहां से आप शुरू करें वहीं से change हो जाएगा. Second point, learning is no longer finding parameters. Learning is no longer finding parameters. Learning is no longer finding parameters. Comma, learning becomes guided quantum states. Learning becomes guided quantum states. Learning becomes guided quantum states. In the bracket, this is not incremental, it is a paradigm shift. This is not incremental, dou by dou x Allah. It is not delta, it is not incremental, it is a paradigm shift. Okay? It's a paradigm shift. Third point, what stays the same? Third point, what stays the same? What stays the same? Stays, S-T-A-Y, ಉಳಿತದೆ, ಏನು ಉಳಿತದೆ? What remains? What remains same? First data set is same. First data set same. In ML it is same, QML it is same. Data set. Second, ground truth tables. Ground truth tables. Third, clinical interpretations. Clinical interpretations. Clinical interpretations. Fourth, evaluation metrics. Evaluation metrics in the bracket accuracy, sensitivity, F1 score, etc. In the bracket accuracy, sensitivity, F1 score, etc. Last point, validation protocols, they also remain same. Validation protocol. How do you validate your research? That also remains same. Validation protocol remains same. Okay. Fourth point. Fourth point. You don't observe the model. You don't observe the model. Previously in machine learning, we observe the model. Okay. We train the model, we observe the model. Is it giving me true, true, false, true? That confusion matrix you create, right? You observe the model. You don't observe the model. You measure outcomes of quantum processes. You measure outcomes of quantum processes. You measure outcomes of quantum processes. In the bracket, it is not mapping, it is physical evolution. It is not mapping, it is physical evolution. Okay. Next point. Problem statement remains same. Problem statement remains same. Problem statement remains same, comma, while theoretical assumptions change. While theoretical assumptions change. Theoretical assumptions change and hypothesis become stronger. And hypothesis becomes stronger. And hypothesis becomes stronger. In the bracket, this is what examiner will look for. This is what examiner will look for. Okay? Your problem statement should be same. Because of quantum, it should not change. You should not say, I will cure cancer with quantum. Okay? ML was detecting, I am also detecting using quantum. Same. Your theoretical assumptions will change. The space will change. Hilbert space will come into picture. But hypothesis will become more stronger. Okay? So this is what examiner will be looking for. They will be looking more of fundamental things. Yeah, that's all. Now I will just read the hypothesis, you can make the difference. The last statement what I have done. These 5 points, what 5 are there?
Yeah, 5.
These 5 points are the points which you can justify to anybody if they try to degrade your work, just you are claiming quantum and you are still doing classical machine learning. Andre, these are the 5 points you have to justify. Okay? You have to talk about this. Now I will read the hypothesis, you will understand the difference. Okay? Hypothesis with machine learning only, it will be ML models can learn discriminate patterns from clinical text data to reliably detect the presence of cancer at any stage. This is the hypothesis. Okay? I will read it again. ML model can learn discriminate patterns from clinical text data to reliably detect presence of cancer at any stage. If you get into quantum ML models can capture non-local and higher order semantic correlations in clinical text data, leading to improved early detection of the cancer. So new term is non-local higher order semantic correlations. That means your hypothesis has become more stronger. This is what you have to claim. Okay? Second hypothesis के बारे में बोल रहा था सर चलेगा. Deep learning models trained on medical imaging data can accurately identify tumor presence and estimate the disease spread. Okay? ML model trained on medical imaging data, because it was image data, can accurately identify the presence and estimate the disease spread. If it is quantum, hybrid classical quantum learning frameworks can model global spatial textural relationship in medical images more effectively, resulting in improved diagnosis accuracy. So this is the improved hypothesis with quantum. So likewise, third is about biomarkers. So underlying assumption here is cancer related patterns are sufficiently representable in classical feature spaces and can be discovered through optimization over model parameters. That is machine learning. In quantum, cancer manifests as latent multimodal structure that can be more effectively revealed through quantum state representations, interference and entanglement than through classical feature-based learning rules. So this is the change in your hypothesis. Okay? Now the last aspect, what changes in the paper? Title में क्या change होगा? Introduction में क्या change होगा? Background में क्या change होगा? Literature survey में क्या change होगा? Results analysis ಅಲ್ಲಿ ಏನು change ಆಗ್ಬೋದು? Discussions ಅಲ್ಲಿ ಏನು change ಆಗ್ಬೋದು? Conclusion ಅಲ್ಲಿ ಏನು change ಆಗ್ಬೋದು? Shall we go ahead with this? Is it making sense? Useful, right? Okay, very good. So next heading, writing a QML cancer detection paper. Next heading, writing a QML cancer detection paper. Writing a QML cancer detection paper. Okay, we will write in this way. एक छोटा इधर column रहेगा, एक कड़े दो column mark. Okay, 2 columns. One is this side, small, that will tell about the section, and these are the comments. So first will be, in a paper, what will be the first? Title. The first is title. Core problems remain same. Core problem remains same. Only the method qualifier changes. Core problem remains same. Only the method qualifier changes. Only the method qualifier changes. That is, ML will become QML. In your title, if it was machine learning, it will become quantum machine. That's all. Only that's all. Nothing more in title. Okay, that is ML changes to QML. एक horizontal line डाल दो /h line according to LaTeX. Okay, next after title I will directly go to introduction because abstract you have to write once you write the paper. Okay, introduction. Next section is introduction. Motivation remains same. Introduction mein you have to explain the motivation. Motivation remains same. Motivation mein bracket early detection saves life. Early detection save lives. That is the motivation for this paper. If there is no motivation, you should not write the paper, right? Early detection save lives. This is the motivation. Okay? Importance of accuracy and precision remains same. Importance of accuracy and precision. Why you have to explain this? Because it is not a medical paper. You have to explain that it is accurate and it is precise. Okay? So importance of accuracy and precision remains same. What you have written there in ML, in QML, it remains same. Okay? Importance of accuracy and precision remains same. Next, role of AI in healthcare remains same. Role of AI. She want to come? Ande. Why? Role of AI in healthcare remains same. Okay. Role of AI in healthcare remains same. So these are the things which remain same in introduction. Now I will tell what changes. A new paragraph introducing ಬೇಗ ಸೆಂಡ್ ಮಾಡಿ ಮೇಡಮ್ ನನ್ನ ಸ್ಕಾಲರ್ ಬರಲಿ ಅವ್ರ ನೋಟ್ಸ್ ಬರ್ಕೊಳ್ಳಿ because she will ask me after 3 days I will not remember. My RAM is very small. A new paragraph introducing the limitations of ML. A new paragraph new paragraph introducing the limitations of ML. Okay, mic क्या तो send करना है. A new paragraph introducing limitations of ML. Okay, so you have to tell the limitations of that. And motivation for QML. And motivation for QML. And motivation for QML as an evolution. And motivation for QML as an evolution, not replacement. As an evolution, not replacement. So समझ में आ गया what changes in introduction? Introduction entirely remains same, but you have to add one paragraph. That paragraph should start with the limitations of ML and then say we need a new technology. Quantum is very promising. In recent days, it has received more traction from all the scientists. They are migrating towards that to get more spatial, temporal data analytics through the existing data. यहाँ पे एक point लिख लो. Reviewer expectation. What reviewer expects? In the introduction, I am reviewer for 7 transactions, IEEE transactions. I have published 135 papers. So I think I can give these comments. Reviewer expectation is, why is quantum needed here? Reviewer expectation, his question will be, he will be irritated because he has done all his PhDs with ML. Now he is reviewing your paper with QML. His ego is hurt. But somewhere he knows that yes, quantum works, but he wants to justify through you. So why is quantum needed here, comma, not just theory? Why is quantum needed here, not just theory? According to Richard Feynman, we can use quantum. No. You need quantization of that answer, justification of that answer. Why QML is required? You have to give in engineering way. Like, this work has used QML and has achieved this much, so we are seeing promising results. Hence, we feel QML can be used. Okay? So, close. Introduction is closed. And once you are done with introduction, you have background. Many people miss this. They directly go to literature survey. But as a reviewer, we expect background always. Because whenever it is a multidisciplinary, if I am an engineering reviewer and I am seeing cancer paper for the first time, I should know what type of cancer you are discussing and what type of cancers are there. Like I reviewed one paper where it was about diabetes. Throughout the paper, I did not understand whether it was for type 1 and type 2. Finally, it was for type 2. And that I diagnosed from the paper. But the writer did not bother to mention that in the background. Okay, so background is very important. Here you will have clinical problem description. In the background only, this side only, you will write clinical problem description. In the background, you will have clinical problem description. Okay, clinical problem description. Background explains about who will die if you don't write this paper. Okay, who will die if you don't write this paper? If you don't write this paper, all the cancer patients whose cancer will be detected in 3rd or 4th stage, they will die. With your paper, it should be detected in 1st stage, early detection. So that you have to bring in here. 4 lakh people are dying because of this. The diagnosis happens only in the 4th stage. Doctors see the images with MRI scan where only they will understand that there is a problem in the 4th stage. Even people are so ignorant that they don't have insurance and they don't do regular checkup. Because of this, mortality is more. Since mortality and morbidity is more, the productivity of the nation is low. And since the productivity of nation is low, the GDP is low. Because of not detection, the human is dying. Because of the human resources dying, the nation is paying the fine for that, the penalty for that. Ye relate karna hai aapko. And if nobody is dying, you should not write this paper. IoT based agriculture, farmers are dying. Okay, defense system, military people are dying. If nobody is dying, no need to do the research. If somebody is dying, we should do research for that. Okay, so clinical data, usme disease background, comma, cancer progression. Be fast. Disease background, comma, cancer progression, comma, importance of text, comma, image, comma, biomarkers data, all remains unchanged. Same, you can copy paste your old paper until it is not plagiarized. Biomarker data all remains unchanged. Keep identical to maintain medical grounding. Keep identical. So all this data, you keep it identical to have a medical grounding. Like on the medical, this paper is not doing some revolution. Only on engineering it is doing. Okay. Keep identical to maintain medical grounding. Next argument in the same background, data set. In the same background, next argument is data set. Data set, comma, pre-processing logic. Data set, comma, pre-processing logic, comma, training, comma, split ratio, 30-40 split, 60-40, 70-30 split ratio, train data, validation data. Okay, train, comma, validation, and split remains unchanged, and split ratio remains unchanged. In the bracket, reviewers like continuity. Reviewers like continuity. Reviewers like continuity. If it is a new paper which I am unable to understand, I will say pass to the next reviewer. Again 3 months. So you should show the continuity. Okay, last argument in the background, evaluation metrics. Last argument in the background, evaluation metrics. Accuracy, evaluation metrics. In that, accuracy, sensitivity, specificity, precision, F1 score, ಫುಲ್ ಒಂದು ಪೇಪರೇ ಬರೆಸ್ತಾ ಇದ್ದೀನಿ ನಾನು. ಎಕ್ನಾಲೇಜ್ಮೆಂಟ್ ಅಲ್ಲಿ ನನ್ನ ಹೆಸರು ಹಾಕ್ಬೇಕು ನೀವೆಲ್ಲ. ವಿಲ್ ಯು ಆಡ್ ಮೈ ನೇಮ್ ಇನ್ ಎಕ್ನಾಲೇಜ್ಮೆಂಟ್? ಅಕ್ಯುರಸಿ, ಸೆನ್ಸಿಟಿವಿಟಿ. Sure. Accuracy, sensitivity, specificity, F1 score. Clinical relevant metrics all remain same. Clinical relevant metrics. Clinical relevant metrics all remain same. Clinical relevant metrics all remain same. In the bracket, changing metrics will raise suspicion. ये ब्रैकेट में जो भी लिख रहे हैं रिव्यूअर के लिए लिख रहे हैं. Changing metrics raises suspicion. Changing metrics raises suspicion. Okay, so we are done with the title, we are done with introduction, we are done with background. There are no major changes. अब से थोड़ा चेंज होने स्टार्ट हो जाएगा. टाइटल में सिर्फ क्यू डाले, इंट्रोडक्शन में 1 paragraph, why ML is limited and what QML can give us. That's all. Now related work. Next horizontal line, उसके बाद में related work. Related work is nothing but your literature review. Okay. ML paper will have, let us be fast, अभी 15 मिनट है. ML paper will have CNN, comma, transformers, comma, ensemble models. Right? These are the things what you see. Ensemble models, comma, feature engineering, and fusion strategies. So these are the things which will be in ML paper. Okay, fusion strategies. QML paper will have quantum ML literature. QML paper will have quantum ML literature. Matlab, what was the first paper on quantum machine learning? What they did, how much they got, accuracy, specificity, and all. Hybrid classical quantum models, comma, hybrid classical quantum models. So, as you said, this is the safest way. You are not working on quantum, you are working on hybrid classical hyphen quantum. Okay, hybrid classical hyphen quantum models. So whenever the reviewer or the examiner they ask, quantum, how can you do that? No, sir, classical only, we are adding 3 bits and getting more accurate data. It's not quantum, don't get offended. Simple hybrid classical quantum machine learning. Next question. Okay, so hybrid classical quantum models, comma, known limitations and gaps. Known limitations, you should declare that only 3 bits are available. The scope of 8 bits is not in this paper, I said. Known limitations and gaps. So this is the new thing. These are the new things which come in your QML paper. Okay. Bracket. What does bracket mean? Reviewer question. How does this compare to existing? How does this compare to existing QML healthcare work? How does your work, right? Ellardu paper okay, nimma paper yak beku anta you have to convince why your paper should be published. So how does this compare to existing QML healthcare work? Okay, done. Next, this is the crux, John, heart of the paper. Methodology. Yahan pe se quantum will come. Next section, methodology / framework. वहां पे ऐसा आप ये भी लिख सकते हैं, लाइक हार्ट ऑफ द पेपर. ओके, थोड़ा दिल बना के, रेड बना के, सो दैट यू रिमेंबर इट फॉर लॉन्ग. ओके, methodology / framework. ML version includes feature extraction, comma, model architecture, So there they will explain CNN levels, Adam optimizer, how they will cut all the layers, whether they are optimizing level. So ML version includes feature extraction, model architecture, training via optimization. Training via optimization. Training via optimization. So this is the ML paper. Hamara QML version must include. QML version must include. QML version must include data encoding into quantum states. Important, huh? Data encoding into quantum states. Data encoding into quantum states. Next, quantum circuit design. They are bullets, huh? Next is quantum circuit design. Then role of superposition, entanglement, interference. Role of superposition, entanglement, interference. Role of superposition, entanglement, interference. Yaad madam? Decoherence conclusion kade baroಣ. We will. Next is measurement strategy. Measurement strategy. Madam is in the right flow. Whenever you want to measure quantum, you have to decohere. Then only you will get one outcome. Okay. So next word is measurement strategy. So that is where you do decoherence. Very correct, madam. Measurement strategy. So quantum will become classical when you do decoherence, because outcome is 0 or 1. Okay, measurement strategy. In the bracket, decoherence. Then hybrid loop. Last is hybrid loop. Hybrid loop मतलब classical से आप quantum कब जाओगे, quantum से classical को कब आओगे? Like classical to quantum, quantum to classical. This you have to explain. Okay, classical to quantum, quantum to classical. Bracket. If this section is weak, the paper will be desk rejected. If this section is weak, then the paper will be rejected by the editor, not by the reviewer. If this section is weak, the paper fails to pass the desk. The paper fails to pass the desk. Okay, so this is about methodology framework. Horizontal line. Next, theoretical foundation. You might have not written in ML papers, but now you have to must write theoretical foundation. Until quantum becomes very common, you have to keep on writing theoretical foundation. Theoretical foundation. The ML will not have any theoretical foundation. If they have, they will have the framework, that's all. QML paper. QML paper needs explicit theory. Needs explicit theory, comma, justify why quantum representation is suitable here. Why quantum representation is suitable here. And explain what structural advantage is hypothesized. Explain what structural advantage is hypothesized. What structural advantage is hypothesized. In the bracket, this is where you explain that quantum helps. This is where you explain why quantum helps or where quantum helps. This is where you explain where quantum helps. Horizontal line. Next section. Experimental design. This is completely new, completely reworked. It has to be redefined. Experimental design. Explain simulator versus real hardware. Explain simulator versus real hardware. Explain simulator versus real hardware, comma, noise models, comma, noise models, comma, number of shots, shot, 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 number of shots. वहां पे नंबर ऑफ एपॉक्स रहता था इन मशीन लर्निंग में, यहां पे शॉट्स, नंबर ऑफ शॉट्स, कॉमा, सर्क्यूट डेप्थ कंस्ट्रेंट, सर्क्यूट डेप्थ कंस्ट्रेंट्स, circuit depth constraint, okay, bracket. Same data set, different experimental logic, bracket, same data set, comma, different experimental logic. Okay. Next, sections that must be added, horizontal line. Next, sections that must be added. Since quantum is not well approved, a foolproof system, you have to add 2 more sections which will help people to accept your paper. I faced this problem in 2018. We started with spin qubits. My first PhD researcher, B.V. Prashant, we worked on spin qubits. Unfortunately, no journal was taking our paper. And finally, we published in multidisciplinary journals. And we didn't get examiner in India. We sent the thesis to Japan physics lab. Luckily, it was much appreciated. They say it is 1 PhD plus 1 MPhil. That much work has been done in that. Okay, so that is why you have to have these sections which will help you to justify. Quantum encoding strategy. Quantum encoding strategy in the bracket, angle, amplitude, wave function. When is the next session starts? 2 o'clock. Can I push up to 12:45? Shall we continue? Huh? Okay. Go to another masjid. 1 baje ka masjid. Quantum encoding strategy bracket में angle encoding, amplitude encoding, basis encoding, angle encoding, amplitude encoding, basis encoding. Madam? Next, why this encoding matches medical data structure? Why this encoding matches medical data structure? Okay, the data is very, very complex. Right? Sputum is a uglu. The kemidaga balgam jo aata hai, that is sputum. And now what kind of data we don't know. Okay, why this encoding matches medical data structure? Why this encoding matches medical data structure? Next, quantum complexity and scalability discussion. You have to do this. Quantum complexity and scalability discussion. Quantum complexity and scalability discussion. This you have to do. In that, qubit limitations, comma, noise sensitivity, qubit limitation, comma, noise sensitivity, comma, near term feasibility. कब तक ये मेडिकल ग्राउंड में आ जाएगा? ओके, नियर टर्म feasibility. When do we implement this in actual medical practice? Okay, that you have to give. Near term feasibility. Bracket में reviewers expect honesty here. Okay, reviewers expect honesty. You should not say tomorrow only they will implement. Once you publish the paper, next day they will implement it medical. Done? And one more paragraph in that. Hybrid architecture discussion. We have this clinical to quantum, right? That is hybrid architecture description. Let us give the description of that. Hybrid architecture description. Hybrid architecture description. In that, classical processing, In that classical processing, you should talk about classical processing, then quantum core, and classical post processing, आप देख रहे हो यहाँ पे क्लासिकल प्री प्रोसेसिंग हो रहा है, क्लासिकल पोस्ट प्रोसेसिंग हो रहा है. Processing is happen only with quantum, that too with core, right? That much is Q. बाकी आपका पूरा ML ही है. Okay? So this if you discuss, then no problem. Horizontal, next results. Horizontal line, next section results. Next section results. Same tables, same metrics. Results, same tables, same metrics. Same tables, same metrics. Accuracy, sensitivity, F1 score, all those things. But interpretation changes. Emphasize structural learning in the interpretation. Emphasize structural learning. Comma, avoid claiming speed up. Okay? Don't ever claim speed with quantum. That is the first example what I have given. Don't tell that bullet train can be replaced by aeroplane. It's a ship. Okay, so avoid claiming speed up. We have speeded the detection. No, for that you don't need quantum. Third point in that, focus on representation benefits. So this is about result. The table remains same, metric remains same, but you have to show what is the advantage of showing encoding interpretation in this, and also focus on representation benefits. Horizontal line, next discussion. ML paper discusses accuracy improvements. ML paper discusses accuracy improvements and model efficiency. ML paper discusses accuracy improvements and model efficiency. This is ML. QML paper discusses what structure was captured. Where QML helped and didn't help, where QML helped and didn't help. Limitations and realism. So this is discussion. Put the line. Don't you see that I am giving you a ready-made paper, or you can write a prompt, create a discussion where it discusses what structure was captured, where QML helped and didn't, and give a separate paragraph on limitations and realism. Kovathara. Next section, conclusion. 3 years is? Madam, Suno madam. She is my PhD student, I am asking. 3 years is not sufficient. Sir, 1 year for coursework, okay? And then 6 months for entire work, define all these things. Once you publish, the journals will take 3 years. Else you have to go for, APC. Article processing charges. If you go with that, open access you can fast. If you know what you are doing, 3 years is not required. If you know what you are doing, I am lucky that I was trained under Shastri, Sandeep Shastri, Jain University. Whatever I am explaining is inception from him. I finished in 2.5 years. They said we cannot give before 3 years. We waited for 6 months. So last is conclusion, right? We are at conclusion. Yeah. Avoid quantum outperforms classical. Avoid quantum performs classical. This is biggest middle class mentality. Okay, I ask my mother any problem, she will say get up at 5, everything will be solved. I say typhoid aa gaya, 5 baje utho sab acha ho jata. So for her everything is getting up at 5. It is correct, but 80%, not everything. Same way we spoiled the reputation of various things, like scriptures also and yoga also, and we say everything is there, but we don't know what is where. Okay, so that is where we go wrong, and we should not do it in research, because this is hum science ke taraf se. So quantum outperforms classical anta endu helbadu, because in last your paper you explained classical has outperformed the previous classical. Okay, prefer saying quantum enhanced the representation. Quantum enhanced representations, show promise in capturing complex multimodal structure. Show promise in capturing multimodal structure. Okay, these are the things you should put in discussion bracket. Tone must be measured and scientific. Tone, T-O-N-E, tone, your words, the words what you choose. This also you can give in the prompt. Let the tone be more scientific and measurable. Tone must be measured and scientific. Okay? I will give you a safer sentence. You use this, your paper will be accepted. This work doesn't replace, this you use even in your 6 months reports, in your DC committee, RC committee also. Okay? This work does not replace classical machine learning. This work doesn't replace classical machine learning, but investigates whether quantum enhanced representations can reveal latent structure, latent, L-A-T-E-N-T, latent structure in cancer data that classical machine learning fails to capture. That classical machine learning fails to capture efficiently and effectively. Efficiently and effectively. Bracket. This helps to avoid desk rejection. This helps to avoid desk rejection. This helps to avoid desk rejection. Okay, you should not claim that quantum is improving. You should say that we want to investigate if quantum helps. Okay. Done? Okay, now I will read just a summary. You make sense out of that. If you want, you can make note wherever you require. Problem statement, same. Data set and matrix, same. Related work, this is ML focused, that is QML focused. Theory, light, there it is strong. So in your QML paper, theory should be strong. Methodology, here it will be classical, there it will be quantum/hybrid. Quantum/hybrid. Experiments, classical training, there it will be state preparation and measurement. Okay. Results, this is accuracy focused, that is structure focused. Okay. This is accuracy focused, that is structure focused. In discussion, we talk about performance here. There we will talk about representations and feasibility. Okay. Representations and feasibility. In conclusion, we will talk about incremental. They got 70%, we got 72%, my student will get 78%. Okay, that is conclusion. But here, exploratory and forward looking. The conclusion will be exploratory and forward looking. So these, just a summary table I have made for this. Now, with this understanding, when you go back to your staff room, you don't feel that you are lost. You can say to your colleague that, Macha, bring your ML paper, I will make QML paper. Okay, and you download QVerse and you will take 3 bits, you will create the circuit and you will get the outcome. And now you create a theory of that, 2 sections you will add, methodology you will add. QML paper is done. Artha hai? Ha. Let it come, let 100 come. Until cancer is detected early and solved, let everybody work on cancer. How, sir?
10 papers are available.
Mm-hmm.
All the 10 papers are cancer.
Okay.
All are
Okay.
Of course, some wordings are changing. All are.
No, methodology should be different. Methodology should be different. Like for example, madam used a spin. She should use angle. Then they might have should use amplitude. And if they both are using amplitude, then whether they are doing it with a trapped ion photon or free electron or spin electron or neutral atom. So methodology change ho jayega, both change hoga. And if it is same, then their title should have not been accepted by that university. They should not accept the title objective if it is same as others. Okay, it is what do you call in patent? You do like pre-search. In patent, before applying for patent, you do one search. Has it been applied already? Pre-search, so that the scholar should take care of that. And if it is repetitive, I will reject it. If angle and angle are used and her performance experimentation is good, her performance is good but validation is poor, then I'll accept this paper. Okay. Last 5 sentences. Do not oversell quantum advantage. Do not oversell quantum advantage. यहीं पे गलती होता है, ये important है. Key takeaways. Key takeaways. This should be your mentality while explaining quantum to examiner and also writing paper. Do not oversell quantum advantage. Key takeaways. Do not oversell quantum advantage. Do not remove classical baselines. Do not remove classical baselines. Do not remove classical baselines. Do not hide limitations. Do not hide limitations. Let me tell you, Stephen Hawking got PhD without proof of his theory. So people love the concept, and that is for what you will be given PhD. Don't hide limitations. Position QML as structural augmentation. Position QML, quantum machine learning, as structural augmentation. Structural augmentation. Emphasize hybrid realism. Emphasize hybrid realism. Keep clinical grounding intact. Keep clinical grounding intact. So hope it was useful. So this was my notes, and this was my notes and this was my PPT. I have completely changed to this because yesterday I learned that few people are PhD scholars and they are looking for PhD and they have got all the fundamentals what they should get. But when they go back to staff room, can they explain, define quantum in a simple means to somebody that I did in the first example? It's a ship. Don't compare with train. Don't compare with car. Okay, that is first basic thing. Second, can you work on quantum? Whatever knowledge you have, can you write a paper? That is done. Can you file a patent on quantum? That matrix is also done. Can you guide on quantum? That also has been taken care of. Now, whenever there is an advancement in technology, you keep on learning that. But other than that, you know the basics, you know the fundamentals, you know how to patent, you know how to write a paper, and you know how to create objectives, how to create a title, and how to write the thesis. So, quantum PhD is ready. Sir, bole jaisa within 3 years. Okay? Now, whenever there is new tool, new simulation, open source, download it, try it. If it is good, write one paper. Have a student team, let them explore that, have more papers. So this is how a teacher can be enhanced from a quantum FDP, and I thought this will benefit you. MATLAB spintronics ke liye, yes, noise reduction, error control, MATLAB, but only one bit which has to be treated as 2 bits. Because you have to have axis in MATLAB. You cannot have only one dimension in MATLAB, 2 axes. Yes, but only 2 bits. Beyond hardware still we have to. So these are the things, and all this structure, I went back to home at 6, I slept at 6:30, got up at 10:30, and then I read all these papers which I have been reading since 2 months and created this structure. It was in rough. So yesterday I created this. Hope this is useful for you. The theoretical plane, empirical plane. Now you understand where it is changing and where it is not changing. Okay? Now, go back to the last page of my printout. Have we diluted reality so deeply? Have we diluted reality so deeply? That means every level we have taken abstract, and finally we confined everything for symbols and notations. Right? Finally, we have abstracted. If somebody is purchasing a flat, they are successful. If somebody is purchasing a car, they are successful. That means we have become the observer, and the measurement is only on this. Have we diluted reality so deeply that either it is 0 or it is 1? That we no longer recognize its original essence. Have we come into classical so much that we have lost our sight over quantum? Okay? It is not about results always, it is about experience. Have you come to FDP? 1. Yes. Have you come to FDP? No. 0. How was the FDP? There is nothing to quantize. That is important. Okay? So have we thinned reality so much that its original fullness no longer touches us? I have written this poem. You have to listen. Have we mistaken the map of the sky, the shore for the ocean? Just by seeing the shore, we felt that it is ocean. The word for the truth, it points toward. Every reel we see, we feel true. We believe the truth only in the words, not in implementation of that. In naming the infinite, did we unknowingly build walls around it? In guarding the tradition, did we forget the vastness of the Creator? The sages did not seek to confine truth. They sought to become transparent to it. The lovers did not worship forms. They dissolved into the beloved beyond all forms, like Mirabai. Truth was never meant to be owned, only entered. We have to enter the truth. We should never achieve truth, or we should never preach truth. We have to enter truth, the realm of truth. The divine was never meant to be reduced to scriptures, but to be recognized in breath, silence, and your existence by being a human being. When the self becomes still, the knower, the known, and the knowing falls away, and what remains is the same one. This is called as collapsing at the measurement, the interference. Everything collapses. Okay, this poem has everything: superposition, entanglement, and interference. Okay, this is collapsing everything to a single 0 or 1 as an outcome. So when the self becomes still, the knower, the known and the knowing fall away, and what remains is the same one. The Vedantic called it as that. The Sufi called love, and the seeker simply calls home. Okay, so this is a poem what I have written. So if you, with the help of ChatGPT also, because my English is not so good, I had written in Hindi, then we made it in English. Madam will correct my Urdu. I will show it to her. This is what I thought that will be useful in the quantum FDP, where we bring it actually to research. So research trends, challenges, and future. 3 words I will give. You can just make a note. Trends, better qubits, hybrid system, real problems. These are the trends. The research trends in quantum, better qubits, that is a trend. कहाँ पे सब लोग invest कर रहे हैं, where everybody is focused. The research trends in quantum is better qubits, like having better students than having more students. Better qubits, comma, hybrid system, classical plus quantum, how do they coexist? This is what people are investigating, companies are investigating, countries are investing on that. Hybrid system, comma, real problems. They are looking for real problems. They don't build the computer and then solve. They take the problem and build a computer. That is the reverse approach in quantum. Okay? Real problems. These are the trends. Next, challenges. ಮತ್ತೆ ಸೆಷನ್ ಟ್ರೆಂಡ್ ಇತ್ತು, ಚಾಲೆಂಜ್ ಇತ್ತು, ಅದೇ ಹೇಳಿಲ್ಲ ಅಂತ ಅನ್ಬಾರ್ದು ಅಂತ ಬರ್ಸ್ತಾ ಇದ್ದೀನಿ. ಚಾಲೆಂಜಸ್, ನಾಯ್ಸ್ ಈಸ್ ದ ಬಿಗ್ಗೆಸ್ಟ್ ಚಾಲೆಂಜ್, ಕಾಮ ಎರರ್ ಕರೆಕ್ಷನ್, ಕಾಮ ಎರರ್ ಕರೆಕ್ಷನ್, comma, engineering scale. Engineering scale. These are the challenges. Matlab, how many wires you can have, how many CPUs you can have, how many processes you can have, batch processing you can do. So engineering scaling, error correction, noise. Future. The future is gradual. It is not sudden. The future is gradual, comma, scientific. Gradual, scientific, and transformative. The future is gradual, it is scientific, and transformative. So thanks for the opportunity. I thank Tabasum Madam for giving me a slot. It helped me to venture. This is the first time I am talking about quantum in front of anybody. This is the first time I am talking about quantum in front of anybody. Other than that, we had our research discussions where we used to just discuss like entanglement, superposition, that to 5 minutes. But as a session, neither UG nor PG, directly to the scholars, directly to the professors. Okay. So if there is any mistake, we will try to prove that it can also be possible in quantum. So thanks for the opportunity. Thanks for staying more with me. So if you go back to college, you show this to your colleagues. Okay, share this with your colleagues. But what you have written, that is a game changer. Don't share it until you publish. You publish, then you can explain it in much better way. Right? The conceptual plane, the theoretical plane, the empirical plane, the bifurcation, construct A, construct B, independent variables, dependent variables, proposition, hypothesis, data encoding. You do it once. You publish one paper. You complete your PhD. Then you explain. Then it will become your information. Without doing that, if you start explaining, you will get stuck. And the real essence of that will not flow to the next listener. Ardha? Thank you. Thank you.
And neither will share this. When we were applying for this proposal, the very first person, as a resource person, which I had in my mind is none other than Dr. Mohammed. Initially, I started with the stage of Ahmed. Then, as you know, it was so challenging to people on this platform, right? And sir was so flexible. I have changed his slot at least 4 to 5 times. You know, he kept on changing because have to give the priority for the distance people. You know, based on their ability, based on their travel, and lot of challenges. Sir was so, flexible. Anything is fine. Last session was fine. Or even actually speaking yesterday, our second half was the final decision, like, gas session, Wednesday afternoon. But, today morning was supposed to be the CDAC visit, right? Since we didn't get the slot, again, the slot has to be yes. So that's how we all are very blessed, to work under this leadership. That's totally different. Today I am not introducing him as a principal, we all know that. But when it comes to knowledge transfer, putting the things in a totally different way, out of the box, sometimes I keep thinking, why I did not think this way? I lose my sleep after listening to him. Why he thinks like this? Why I don't think in this direction? I could have also said, but I have corrected myself. A lot. Yesterday, we were interacting maybe not
Yeah, 2
hours.
midnight.
Midnight discussing.
I was making these notes completely changed.
I saw the online.
I said, Madam, I want whiteboard, no PPT.
So, this is only technical perspective what you have discussed. Half of the things I was working on, I was using examination and other arrangements. But the video is there, it's going to be with all of us. Repeatedly, we are going to watch this. That's it. So, I don't know whether he touched the spirituality or not, but the other day sir was saying, wherever I am going, 360 degree, I take to the quantum journey and guiding up to attain spirituality. Right? So, it's too good to map every bit by bit of quantum to the spirituality, to the creator. Right? So, sir, we should have some extended session where
My knowledge
not technically, a non-technical session where we can understand it still better quantum, with a different perspective, right? So thank you so much. It was a great session, sir. And you are thanking me, but I should thank you at the same time. I'm sorry for that. I had sleepless,
2 months.
And it is not only the nights. I'm very sure that 24/7, back he was preparing. The flow he has changed, multiple times. And today's flow was amazing. The way you started and the way you closed. That is very essential. Thank you so much.
Thank you.
I would like to extend thank you.
ನನ್ನ ತಮ್ಮ ಅವನಿಗಾಗಿ ಏನೂ ತಗೊಳ್ಳಲ್ಲ, ಅದಕ್ಕೆ ನಾನು ಅವನಿಗೆ ಇದು ಬೈ ಮಾಡಿದೆ. ಅವ್ನು ಯಾವತ್ತೂ ಕಂಪ್ಲೇಂಟ್ ಮಾಡಲ್ಲ, ಆದರೆ ಎವ್ರಿ ಡೇ
Emphasize structural learning. Emphasize structural learning. Comma, avoid claiming speed up. Okay? Don't ever claim speed with quantum. That is the first example what I have given. Don't tell that bullet train can be replaced by aeroplane. It's a ship. Okay, so avoid claiming speed up. We have speeded the detection. No, for that you don't need quantum. Third point in that, focus on representation benefits. Focus on representation benefits. Focus on representation benefits. So this is about result. The table remains same, metric remains same, but you have to show what is the advantage of showing encoding interpretation in this, and also focus on the representation benefits. Horizontal line. Next discussion. Discussion. ML paper discusses. ML paper discusses. ML paper discusses accuracy improvements. ML paper discusses accuracy improvements and model efficiency. ML paper discusses accuracy improvements and model efficiency. Accuracy improvements and model efficiency. This is ML. QML paper discusses what structure was captured. What structure was captured? Where QML helped and didn't help, comma, where QML helped and didn't help, where QML helped and didn't help, comma, limitations and realism, limitations and realism. So this is discussion. Put the line. Don't you see that I am giving you a ready-made paper, or you can write a prompt, create a discussion where you discuss what structure was captured, where QML helped and didn't, and give a separate paragraph on limitations and realism. Kovathana. Next section, conclusion. 3 years is? Madam, Suno madam? She is my PhD student, I am asking. 3 years is not sufficient. Sir, 1 year for coursework, okay? And then 6 months for entire work, define all these things. Once you publish, the journals will take 3 years. Else you have to go for ABC. Article processing charges. If you go with that, open access you can pass. If you know what you are doing, 3 years is not required. If you know what you are doing, I am lucky that I was trained under Shastri, Sandeep Shastri, Jain University. Whatever I am explaining is inception from him. I finished in 2.5 years. They said we cannot give before 3 years. We waited for 6 months. So last is conclusion, right? We are at conclusion. Yeah. Avoid quantum outperforms classical. Avoid quantum outperforms classical. This is biggest middle class mentality. Okay, I ask my mother for any problem, she will say get up at 5, everything will be solved. say typhoid आ गया 5 बजे उठो सब अच्छा हो जाता है. So for her everything is getting a bit fine. It is correct, but 80%, not everything. Same way we spoiled the reputation of various things, like scriptures also and yoga also, and we say everything is there, but we don't know what is where. Okay, so that is where we go wrong, and we should not do it in research because this is our, हम science की तरफ से. So quantum outperforms classical ಅಂತ ಎಂದು ಹೇಳಬಾರ್ದು because in last your paper you explained classical has outperformed the previous classical. Okay, prefer saying quantum enhanced the representation. Quantum enhanced
administration. She began her academic career in 2004 as a lecturer and has since served in various education institutions across India, gaining rich exposure on undergraduate, postgraduate, and research levels. Dr. Thilagavathy has significant experience in conducting and contributing to faculty development programs, workshops, and technical training sessions, and has actively participated as a resource person, program committee member, and a session chair in several national and international events. Her research contributions include more than 25 publications in reputed journals and conferences. She has also published 4 patent proposals in the Patent Office Journal India and has been awarded 1 design patent. In addition to research publications, she has authored 5 textbooks and contributed more than 10 book chapters in edited volumes published by reputed publishers. She has received Professional Excellence Recognition from Kismet Global Summer School for the years 2024 and 25, highlighting her expertise and active engagement in emerging areas of quantum technologies. She is a professional member of ACL and CSI and a lifetime member of ISC. Her areas of specializations include text mining, NLP, artificial intelligence, and quantum computing, with strong emphasis on hands-on learning and interdisciplinary applications and research-related skill development. We are truly happy to have you with us today, ma'am. Let's give a big round of applause to ma'am. I now request Dr. Ahmed from the Dean of this FDP to kindly welcome our guests.
That's a lot. Help madam to check ये ऑन करो check Ma'am, 1 minute. Can I help you? This also. Just. Cordless, sir. Ma'am, are you comfortable holding this in your hand?
On it.
Yeah. Otherwise, this?
Yeah, better I will use that. For this, is this needed?
Yeah.
Okay. Yeah, that board, one board was. Okay, no problem. Okay, no problem. I will use one document here. Okay, fine. Thanks for the warm welcome and thank you for inviting me as a resource person for this FDP. It's my pleasure to be here. And the topic given to me is quantum machine learning and optimization. So everyone is looking for like what is the next step in machine learning, because we all running behind machine learning for the years, for more than 2 decades, and we are looking for what is the new like a new thing we can go for in by using quantum machine learning. So actually, like from the previous sessions, you will have some sufficient background knowledge about quantum mechanics. right? There are few properties with quantum mechanics. With that few properties only, we are playing with different fields by including the quantum technologies. So the main properties that I just want to reveal those properties, like, so like the main thing is superposition. So if you are classically, if you are going, like we are saying like we have parallel computing, everything is there, but actually there is no parallel computation is happening in our classical processor. So the thing is, we are adding more number of processor and we are giving, like we are executing a number of instructions parallelly with each and every processor. So if you are considering a single processor, it is going in a sequential manner only. So that's what like we are, people are thinking that, so we have some predefined space for the chip, like already it is became nano, in some nano measurements, right? Like the chip size became that much tiny. So if they are reducing some particular element even more than that, so automatically it will start behaving in a quantum way. Right, so that's what people are looking for alternative. So because like we are every day, like we are going with more and more advancement in technology, the amount of data we are dealing with is greatly evolving every day. So people are looking for alternative thing. So what is the other way of computing? So that's what people shown interest in quantum computing. Actually this thing is introduced by physicists before the Second World War. After that, they have been involved in different activities. So again, like when this point comes, like when people are worrying about like, so we can't reduce the chip size even more, then what is the next point? So then they have taken the concept of those people. Then they started working on it. So as we are having enough technologies nowadays, so we are keep on moving, like moving in quantum way drastically. Like people are involving in different domains of quantum research. So coming to the quantum machine learning, so it's going to be a hybrid approach. Like we are in NISQ era, noisy intermittent state. So we don't have an error-free quantum computer. Like still we are, most of the time we are using simulators. Simulators, like it won't get affected by noise, right? Because when it comes to the real quantum computer only, we need to worry about the noise and all. So using the real quantum computer also, like a few giants, they developed some quantum computer, but it is not practically feasible for us to make use of it, because we are not that much money. We are not having that much money to make use of that. Okay, so we are going with now, and one more thing I want to tell in this stages, like quantum computing is not going to replace classical computing. Classical computing will exist ever. Only the quantum computing is going to help the classical computer when in the situations where the classical computer will struggles to deal with huge amount of information, or when it struggles to deal with complex problems. So it is going to cooperate with the classical computer. So in another terms, if I want to say, if your problem is a p-type problem, classical computer will be the perfect choice to deal with that problem. Even if you are converting that p-type problem to quantum computer also, it won't give you any performance benefit. Only classical computer will do nicely. So that's what it is advisable to go for NP hard problems for quantum computer. That too, we don't have any proof that whether quantum computer will solve all NP hard problem. That is a big question mark. We are keep on trying. So everything is going in a trial and error basis method. So when come to quantum machine learning, so it combines quantum computing with machine learning concepts. So either we are going to use either quantum algorithm or hardware to perform the learning task. So So either it can deal with classical data or quantum data. So again, the quantum data can be generated by some quantum sensors. So there are some sources of quantum. So from that we need to take the data. So obviously there is no need of like encoding. If we are directly using quantum data, directly we can use it. But again, like now we are as already we are working with classical data. Now we are looking for the opportunity that whether we can bring in the quantum here. Okay, so most of the today's QML techniques are based on hybrid approach. So what motivates us to move to quantum machine learning? So as I said, classical machine learning is struggling for complex problems like NP-hard problem, like optimization problems. Okay, so and then dealing with large data set, or when you are moving from high dimensional, like a low dimensional environment to high dimensional environment, the computation will be exponentially growing. Okay, so if you are using a two-dimensional thing, like it will be n square times. So if you are adding one more dimension, it will be like growing in an exponential manner. But whereas in quantum, we have the feature called, which feature will help in quantum to explore more number of states. Superposition. Okay, so by including a single qubit, so if I have one qubit, I can explore 2 states. If I have 2 qubit, I can explore 4 states. If I have 3, 8 states. So here adding a one qubit will increase the state exploration to 2 power n. Okay, so in that way, the quantum is playing a major role in helping this machine learning applications. No, we are not going to we are going to use the ML thing, we are not going to change the entire thing into quantum way. So only the learning part, whichever thing is complex. So only that portion alone we are going to replace the quantum circuits. So deciding about the optimization part will be handled by classical optimizer only. So only thing is when you want to explore more number of features. So classically if you deal with it, it takes more computation. So the number of features are huge. Sometimes your classical computer will struck. So in that environment only we are going with this quantum. So then once you did the measurement from the quantum circuit, then again you are feeding that to classical optimizer, classical algorithms for make the decision. Because making the decision from the input, it is a p-type problem. It won't take much time. So we are whichever part, we are going to break down our entire problem into different phases. Whichever phase are complex, only those phases only we are introducing quantum thing. Yeah, a Hilbert space is nothing but the number of mathematical space, the number of possible states. So if I have one qubit system, the possible states are 2. 2 means 4, it's a Hilbert space. Have you heard about block sphere? So the block sphere can have, you can have unlimited number of states in a block sphere. It's a 2-dimensional sphere. So that's what we are saying, Hilbert space, the possible number of states. Okay, so through this superposition, we can explore how as much number of states. Then coming to the types of quantum machine learning, either it can be a quantum enhanced method or it can be a quantum inspired ML. Quantum enhanced means the one I said earlier, data will be classical and we are using some quantum circuits to process that classical data to get some output. So, and then quantum inspired means we are trying to imitate the quantum nature through some classical coding. Classical algorithms are written to imitate the quantum nature. So that is quantum inspired ML, and fully quantum means both are algorithm also quantum and data also quantum. So still we didn't reach that one. So we are currently we are working with that quantum enhanced ML and quantum inspired ML only. Yeah, quantum enhanced ML means like your QSVM and the QA, VQE, all these things are coming under quantum enhanced. Like you are taking the classical data and you are doing the encoding to map that classical data into the quantum state, and then you are exploring the different possible state transformations through the quantum circuit, and then finally you are making the decision by using classical module. So here data is classical one, and you are processing the data through quantum circuits. And the comparison between classical and quantum ML in terms of scalability. So your classical ML is struggling with high dimensional things. So it's poor for high dimension. And your quantum ML is doing good in high dimensional spaces because of that superposition. And then coming to the optimization problem. So most of the classical ML algorithms struck with local minima. So, you know, in optimization, what would be the target? What is the goal? So we need to find the lowest value, lowest cost, value for the cost function. So that is our goal, right? Our lowest error rate. So that is our goal. So in classical ML, sometimes it will struck with local minima. So it feels that that is the global optimal solution, but practically speaking, it won't be the global thing. So there will be some other deeper region will be there, but we are unable to know, we are unable to explore the next thing, because we feel that in that particular situation, so that will be the lowest thing. So we feel that that is the global optimum. So that kind of things we struck sometimes. But whereas in quantum ML, so we never got into that local optimal solution. We will get into the global optimum. So the property which is helping us is tunneling, right? It is a quantum mechanical property. So naturally, if you observe any particle, so there won't be whatever barrier comes in between, it will pass through. But classical ML, we are writing the code and we are doing everything, but in quantum, it is working based upon the nature. So according to nature, even if I am kicking this board also, there will be some whatever energy I am giving this side, I can phase it in the other side also. So that is tunneling. So it won't none of the barrier will stop the movement of the particle or the flow of the energy. That is tunneling. Okay, so because of that property, your quantum particles will reach to the global optimal solution. So always it will give you the global optimal. And then coming to the kernel methods. So kernel methods, mainly in which situation we are using in classical ML, when we want to project the data into high dimensional spaces, that time we are making use of kernels. So projecting the data into high dimensional space will consume more time, right? So more computation also it will take. So but whereas in quantum ML, it is resolved by using that superposition, entanglement and all. And data representation, classical will require large memory, but in quantum, it doesn't need that much memory. And yeah, you can go through that sampling, it will take taking the particular samples out of huge volume is consumes more time, or sometimes it is very hard to take it. Okay, and energy wise, it consumes, classical thing will consume high energy cost, and this quantum ML will consume less one, because we are using less resources here. And if you want to express a huge problem or very complex problem, here we need large models. Okay, so if we need large models, obviously it need a lot of resources, a lot of memory will be needed, a lot of computation will be needed. But here it is very compact and highly expressive. Okay, so all these things, like whether practically we are achieving all these things here in quantum means, again we are struggling because we are in NISC era, right? Once our quantum computer is fully evolved, then we can surely say we achieved all these things. And I think you know about qubits, right? In classically we are saying bits, and the equivalent here is qubits. So the difference between classical bit and qubit is, classically we say like, we will say it is true or false, right? So if you are doing one computation, either it will end up in true state or end up in false state. But whereas in quantum, like it is a probability based system. So always like all the states are having some probability. So naturally, if you are saying like it doesn't, like everything is having some probability. Like we are going with the maximum probability when we are taking it. So the qubits represented by using this Ket notation called alpha Ket 0 and beta Ket 1. This is a single qubit representation. So alpha represents the amplitude of being in a state Ket 0, and beta represents the amplitude of being in a state Ket 1. Okay. I think you know the normalization property and all, people would have taught you, right? So if it satisfies, if any quantum, if you want to say any state is quantum state, that should satisfy the normalization property, otherwise it won't be a quantum state. And the role of entanglement in QML. Okay, so like when we are sometimes in ML model, we want to find the correlation between the different features, like how they are correlating, supporting features and all those things. So classically, like we can't evolve all the correlations, but here in quantum way, if you are making the entanglement between those qubit lines, so you can explore all the hidden correlations. Because we are not going to do anything, like it is automatically correlating, so it will discover all the hidden correlation between the futures. Okay. So the thing is like we are designing a circuit, but we are making the circuit to work in nature way. So in nature, like we can think that all the objects are independent, but now if you deeply observe, everything is correlating. If you think about this galaxy, all the planets are correlating with each other. So likewise, only here also, like correlation means like it will be positive correlation and negative correlations. So have you heard about that Bell states? So if two qubits are positively correlating means like if I know the state of one particular state, I need not have to measure the state of the other qubit. So yeah, the same, like if they are positively correlating, if I am measuring 0, the other person also will measure 0. Okay, if it is negatively correlating, if I am measuring 0, obviously the other person is 1. So in that way, if two futures are correlating, then like you can reduce the measurement also. You need not have to measure the other one. If I say two qubits are correlating, because measurement is another one costly thing in quantum computing. So it consumes it is the costliest thing in quantum circuits, measurement. So we can reduce the number of measurements. If I have 4 qubits, so out of that 4 qubits, 2 qubits are correlating, then I need not have to do 4 measurements. I can stop with 3 measurements, because the 2 correlating thing, like if I do 1 measurement, then I can estimate the other one. So using this property only, like people are doing the like a satellite, like without having anything. So they are doing teleportation and all, right? So I think you would have heard about that experiment also, China's experiment.
So if it's feature correlation, so now I mean to say if you use more number of qubits, then searching for a correlation between the features will be reduces, or how?
No, the correlations you will discover more, sir, and also you will reduce the number of, like if you found that the two qubits are correlating, the measurement also will get reduced.
Okay, machine learning, so where that is the correlation between the features, right?
Yeah, here like something we know, sir, like how these two features will correlate. But if you are working with the quantum nature, no. So the unexpected correlations also you will get to know at the end. So, but that we can't say, because when the qubit is acting in a quantum way, so we can't know, we can't say in which state it is. So what could be the amplitude of Ket0 state, Ket1 state? When we do the interference through the measurement, that time it will rest in some states. Then only we will come to know it end in this particular state. So until the qubits are working in the quantum way, we can't say like in which state it is, how they are behaving. So that's what people are struggling, like the decoherence time, you know, right? So how long we can make the qubit to work in a quantum, like we can control the movement of the particle, quantum particle. So that is the coherence time, so the decoherence time. So if it is say like 1 millisecond, so that means that I can hold the control of the qubit for 1 nanosecond. After that it won't be in my control, it will behave on its own. So that's what, like for doing the complex calculations, if we want to have very lengthy circuits, it need more coherence time. So that's what people are struggling, like they can't hold the control of the qubit for a long time for doing the long computations. That is also the other point where we are struggling now. Then quantum data, like we have some quantum sources, like through quantum sensors also we can get the data directly as a quantum thing, or otherwise if we are using classical thing, we can go with encoding scheme. I think people said these things are already covered, the different encoding schemes to convert the classical data into the quantum state. Okay, either you can go with basic encoding. Suppose if you are having a bit string of some limited size, you can directly go for basic encoding, like whatever, if your bit is 1 and you can map it to Ket1, if your bit is 0 then you can map it to Ket0. So if the string size is minimal, so you can go for basic encoding, or otherwise amplitude encoding. If you are having a vector thing, then you can map it to the amplitudes of the qubit. And angle encoding, like we will be using a rotation gates based on some particular axis, either based on the x-axis, y-axis, z-axis. Again, deciding which rotation gate needs to be applied, it's based on the problem specific thing. So we need to understand our problem, based on our problem, like which rotation is needed, that we have to decide. So like how the quantum computing helps the classical machine learning means it is speeding up the learning algorithm. That is, learning process is got speeded up because of that superposition. Through superposition, we can do lot of parallel computations. And challenges in QML is again noisy thing. Even if you are using a quantum circuit, so if your circuit is lengthy, then due to the heat, the noise will be arised, or due to the environment, noise will be there. So if noise is more, your qubit won't act as per your expectation. You can't get any fruitful outcome from the particle movement. And then we are having limited qubits. So if we want to map each and every feature with 1 qubit, then if your problem statement is having millions of millions of features, we don't have that much sufficient qubits as of now. So that is the another point. So limited qubits is also pulling down the performance of QML as of now. And then barren plateau. Like in optimization problem, if the structure is curvy structure, then we will keep on looking for the lowest cost. We can keep on searching for the next theta value or next, like we can estimate the next cost function value. So the next parameter to iterate our circuit. But if the plateau is like flat, then everything is having looking like same. So we can't find like any more lowest point. So we don't have any path to move further in the optimization process. So we will stop our learning in that stage. That is barren plateau. So that's all the basic about QML, like what is QML, why we need it. Then we are moving to optimization in ML. Like generally you know about optimization problems, so finding the best solution for your problem. So you, like there will be multiple solutions for your problem. So among the multiple solutions, we need to find out the best one. So that is the optimization. So generally we will define the optimization function, optimization problem in terms of cost function. So we want to get the lowest cost value. Okay. So the important property playing, the quantum property playing role in this optimization problem are superposition and interference. So as you know, superposition is helping us to represent all possible solutions. So classically, if you are going with classical ML, for every solution, so like in each and every computation, you will explore about one solution. Then you need to do a comparison and then you need to come with the best one. But whereas here, parallelly, we are exploring all the solutions and we can come out with the best solutions in a single, that means like in few number of iterations. So that's what the complexity and amount of data involved is rising in in today's era. So the classical optimization is struggling to get the best outcome or to process that much huge data. So this is the normal thing, like so you will be forming the expectation value and everything, the loss function, everything, and then the classical optimizer will update the circuit with the parameters, like what could be the next parameter to move to the next iteration of the quantum circuit. So this loop will continue until you are getting the best choice. So before going to design the circuit, quantum circuit for the optimization problem, first thing what you have to do is you need to convert the problem into the mathematical equation. Then that mathematical equation needs to be converted into the quantum thing. That means it should be converted into the Hamiltonian. Okay, so Hamiltonian is the energy function of which is represented in the way of quantum. Okay, so the representation of the problem should be given in the form of QBO. It's nothing but quadratic unconstrained binary optimization thing. So here I have taken one example problem, the traveling salesman problem, as an example. So when it comes to optimization problem, the goal will be set and the lot of constraints also will be given. Your problem have to find the goal by following all the constraints. If any of your solution is not following the constraints, then it should have some impact in the cost function, right? So like that, we need to form the QBO here. So here the objective is, in traveling salesman, we need to find the shortest closed path between a set of entities, right? So that is the traveling salesman problem. So, and the first constraint is every site in S is nothing but the set of all cities. Okay, every site in S should appear in the path and no site is visited more than once. This is, I think everyone knows about traveling salesman problem, right?
Can you just put some time to this QBO representation?
Yes, ma'am.
QBO representation. What is that?
No, like actually we can't directly represent the classical problem into the quantum energy state, right? So for that we need a mathematical, all the classical problem needs to be converted into the mathematical representation. That mathematical equation only will be converted into the quantum energy thing, the Hamiltonian.
So in general that represents...
Yeah, generally for all the optimization problem, you need to follow this process. First, you need to form the QBO. then this cubo will be represented as a Hamiltonian. Okay, so here this is the cost function. So first one is like it is the sum of all the weights of all the parts, and then this portion is the representing the constraint 1. So here every site in S should appear in the path, right? Okay, so here we are checking like if everything is appears, like this sum will get 1. Right? If a particular city is appearing, then that will have some 1 value. So if you are adding up all these things, it will also become 1. So in that case, so we have the overall combination is 1. So if all the cities are appearing, this summation also will become 1. 1 minus 1, 0. So we won't have any added weightage in this cost function because of the first constraint. So the lambda is the penalty. Okay, if I am not obeying this first constraint, so I will get some value here. So I won't get 0. So I will get some positive values here. Okay, so we will always fix this lambda as a greater positive value so that it will have highest impact in the cost function. So if I am choosing that particular choice, then it won't give the least cost function. So it will be something greater than what I am having now. Okay, and the second portion is representing the second constraint. No site is visited more than once. So that also we are having here. Okay, if a particular site is visited more than once, then it will have some more, it won't give 0. It will be some positive number, so that weightage also will be added. So whenever I am choosing, like here we are exploring all the possible combinations, right? So if a combination, if I am taking like one possible solution, like which is not satisfying any of this constraint, surely I won't get the lowest cost. So the solution which I am taking is satisfying these two constraints will have the minimal cost function. So like that, whichever optimization problem comes, so you need to calculate the weight of the normal, for the goal you need to find out the weight, and then whatever constraint is given, that constraint also should be like converted into one of the particular component in the cost function. Okay. Then after we convert the cubo into the Hamiltonian, then we can go with any quantum circuits, like we can deal this optimization in 2 ways. So one method is quantum annealing method and another method is circuit based method or gate based quantum computing. Okay, so annealing, like you heard about D-wave, right? So D-wave is like they have done so many number of optimization problems by using this annealing technique. So here what they will do is, I think I have that also. So annealing is mainly working based on the entanglement and tunneling property, and the main concept behind this is adiabatic theorem. The theorem followed by this quantum annealing is the adiabatic theorem. So according to adiabatic theorem, what it says is, so if we are moving any particle in a very drastic manner, it will never lead you to the optimal solution. Okay, if we are gradually slowing down the energy, then it will rest in the place where you have very deeper place. Okay, if you are like increasing the speed, like if the particle speed is very high, then it won't rest in that lowest region. Okay, if you are slowly moving, like I think we know the game, right? We need to fit the ball, like there will be like a maze and we need to move the ball into the center, right? So in that, if you are moving it slightly faster, we won't get it, right? So we need to slow the speed of that balls, right? Like this here also, we will start with some random energy mapping, like initially we will set some energy level for the particle, then gradually we are reducing the energy, so it will rest into some lowest level. So after that, even if you are reducing also energy also, it won't go beyond that. So we can confirm that that is the optimal solution. So that is the concept followed by QA-OA algorithm. So it's based on the quantum annealing. So it's here. So this is what the classical algorithms are structuring in the classical ML algorithm. When we are moving the particles, like sometimes we struck with local minima. So in this region, there is a big hill over here. So I can't see the lowest part after this particular hill, right? So I fix that in this particular situation. I fix that this is the optimal solution, but it is not the optimal one. This is the optimal one. So the classical algorithm is structuring in the local optimal solution, whereas in like a quantum way, so it will penetrate through whatever barrier comes. It will penetrate through the barrier. Classically, like what we will do, if suppose if we struck in the local optimum, we will give some high force to jump into the hill. Like if we want to go in the next side of this hill, we need to give some force, then it will move to the next side. But in nature, in quantum nature, it will pass through. Okay, so there is no need of external force to make the particle to jump. Okay. This is the concept behind QA-OA algorithm. Okay. Then gate-based quantum computing, so it will have like a series of quantum gates are placed as a circuit, and then the qubits are initialized to some initial random state, and then like the gates are doing the state transformation, and finally you will do measurement and you will get some value. Okay, so this is how the gate-based quantum computing solves the optimization problem. And the hybrid approach, either it is a VQE or QA-OA. So first, what we need to do is we need to do the encoding. That is, we need to map our classical information to the Hamiltonian, and like that is QBO or Ising. So Ising means energy level. So QBO, as I said, it's a representation, the mathematical representation. Then we are going for quantum circuits. We need to construct the quantum circuit. So the quantum circuits, it's a German word, Ansatz, right? So we need to create a quantum circuit, and the circuit, like your initial state preparation will be passed through this circuit, and a lot of state transformation will happen, and finally you will prepare some output state, and you will do the measurement. After the measurement, it will become a classical data that you know, right? So whenever we do a measurement to qubit, so it will rest to any of the one state, right? If I am disturbing the movement of, if this fan is running, if I am giving a fast force, like if I am keeping a stick in between, the fan will rest, right? So it will be resting in any one of the state. So that is the thing we are doing as a measurement. So after the measurement, some matrix representation will be, the feature map will be there, and that will be fed to the classical optimizer, and the classical optimizer will look for the new parameter. It will construct the new theta value for the next iteration, so that it will keep on, this step is repeating again and again. Okay, this circuits here, the quantum circuits, or some of the circuits are parameterized circuits. So those parameters are updated in each and every iteration. So this iteration will continue until you are getting the best solution. So the two primary algorithms, the optimization algorithms, are QA-OA, quantum approximation optimization algorithm, and variational quantum eigensolver. So the advantages are, the superposition make us to explore multiple solutions simultaneously, and then interference. So here the constructive interference is there, destructive interference is there. Constructive interference will enhance the amplitude. Okay, if a particular solution is correct, and if other particles are having a constructive interference with that particle, then it will increase the amplitude. Yeah. So if it is destructive amplitude, means they will cancel out the amplitudes. Okay, so in that way, the interference is helping us to boost the amplitude of the correct solution. Then The purpose of QA, it's a hybrid quantum classical algorithm. It is used to solve the optimization problems like traveling salesman problem, max cut problem and all. And in this NISC era, so these two like QA, OA and VQA are some of the promising algorithm which is doing good in some of the problems. We can't say it is doing good in all the problems. Still, we are lagging. For some problems, it is not giving best answer. And also, again, the practical difficulty is we don't have that much resources as of now. So the qubits is less, and also accessing the real quantum computer is not practically feasible for us. So we are doing research with minimal data set, very minimal data set. In that minimal data, like when you want to realize the quantum advantage, you have to work with the huge volume of data. If you are like, as of now, practically we are not having that thing, we don't have that facility as of now. So what we are doing, we are reducing, because in my laptop, the processor is having some capability, right? Within that capability, if I want to get some output, I will be having very minimal futures, 2 futures, 1 futures. So if we are reducing the futures like that, so we can't experience the quantum advantage. Your classical ML will give good result. They are giving 80%, 90% of the accuracy, but the QA, OA and VQA is giving 60, 65, like that only they are giving. Because if you want to realize the quantum advantage, you have to deal with the complex environment. Then only you can realize it. If you are having very minimal set, classical itself is enough for that. There is no need of quantum.
This will be the simulation side of the
yeah, even in simulation also, we are trying to imitate the quantum nature, but where we are running in the classical processor. So the hardware is not supporting, no. Okay. So the problem the QA deals is about that like the combinatorial problems. Like the best example is, well-known example is traveling salesman or the max-cut problem. It's a graph algorithm, where you want to make a single cut which cuts the maximum number of edges. It needs to split the graph into 2 portions by cutting the maximum edges by a single cut. So that is the goal of max cut problem. So all these are coming under this combinatorial problem. So here, if you are adding in a graph, if you are adding a single node, then it is it is growing exponentially, right? So the possible combinations are growing exponentially. If I have only 2 cities, possible path combination is 1. If I have 3, so like that, whenever I am adding a new city, the possible combinations are growing exponentially. So, so that will be dealt effectively by using this QA-OA algorithm. And to start with this, as I said earlier, these problems should be mapped to the Ising model. That is, Ising model is nothing but energy. So we need to convert the problem into some energy, the starting point. And also we need to estimate what could be the estimated lowest energy state, what we are expecting. So the physics inspiration is because your QA-OA is following the adiabatic theorem. As I said, the slow evolution will give you the perfect results. So actually, here, when we are having a circuit for QA-OA, we can't practically doing that slow reduction of the energy. For that, what they are doing, they are having switching, they have 2 layers that the alternative layers they will be having, and they are doing switching front and forth of thing. So that automatically the energy will get reduced gradually. So that pattern they are following. So how this QA works means like here I mentioned like each and every step works based on which computing. So the first one, guessing the initial parameter, is done using your classical way, and then runs the circuit using those parameter is done by using your QPU and measuring the results QPU, and after the measurement it will be a classical result. Then your CPU will calculate the energy of that result, and then your optimizer, classical optimizer, will update the value, the parameters gamma and beta. So this loop will continue. So as I said earlier, here the two layers are repeated continuously. Okay, so why this will be continued means like to reduce the energy. Okay, suppose if we have a ball, like if we are doing front and back like that, then automatically slowly that energy level will get reduced. So that is the thing they are trying in this circuit. So initially, to make the state into the superposition, Hadamard gate will be applied. Then after, with that superpositioned state, like you are exploring all the possible combinations, right? Then you are feeding that into the cost layer and the mixture layer. So the responsibility of the cost layer, cost means like it is nothing but the problem Hamiltonian. It applies the phases to the state based on their cost, and it marks the good solution. So it is trying to, in that particular point of view, which is the best solution. So it marks that best solution. That is the responsibility of this first layer. And then the mixer Hamiltonian, that is the second one. So the responsibility of this one is, it facilitates the transition between different states and allowing the algorithm to explore the solution space. So it is allowing to explore all the possible solutions in the given feature space. So the first layer is what it does, it is marking the solution. So in that particular point of time, so which is the best solution, that marking will be done by that problem Hamiltonian, and the mixer Hamiltonian will do the state transformation, and it is trying to, like it is helping to explore all the possible solution space. Once you've done the measurement, then the classical output is given to the classical optimizer, and it will calculate the expected objective value, and it will calculate the new measure for that alpha and beta. That will be given back to the quantum circuit again.
Just repetition, they are making to get a proper optimization.
Yeah, the thing, still there is no further reduction in the cost function. So they are repeating it again, or otherwise still they are like, they will have some expected optimal result. No, still they are achieving that, they will repeat. So how this QA is dealing that max cut problem is given. So the goal is to split the graph into two colors to maximize the number of edges connecting the different colors. That means like if you have different set of, like the nodes are colored red and black like that. So you need to split that into two partition by splitting the graph with single cut, so that the maximum number of edges should be cut down. So here the first step is encode the graph into the qubits. So that means here each and every node in the graph is mapped to the qubit. And step 2, here applying the Hadamard gate, it will create the superposition of all the possible combinations. Then apply the problem layer. So here we need to mark the good cut, right? So we need to mark which cut will be the possible one that we are marking it in the problem layer. And in the mixing layer, so we do interfere states to amplify the probability of the best one. Okay, so in the mixing, what it tries, like it is exploring all the possible feature space, and what it does, like when we are exploring it, automatically interference will happen. So there will be a positive interference, like a constructive interference, destructive interference. So constructive interference will enhance the amplitude of the best result. Destructive will demolish the amplitude of the false states. And finally, the measurement will give you the bit string, which is the proposed solution. Okay, so here I didn't mention the iteration. Actually, this won't be done in a single execution. So it will be continued for multiple times. Iteration will follow. So advantages and disadvantages of QA-OA. When it comes to advantages, it can represent more number of states, but where the classical RAM is not enough to hold that many states, because we are not going to store all the state. Okay, so we are not going to record all the state. Classically, if you are doing, we are registering all the states, we are recording all the states. So we need more memory. But whereas here, everything is just like we are assuming that it is working in that way. The nature is working in that way. So we are not registering all the states. Only whatever we do measurement, only that one only we are recording. Okay, so it doesn't need that much memory, and speed also it's very high, because we are doing a real parallel computation here. So either it will be exponentially faster or quadratic speed up also it will give. And it is a hybrid nature, makes it somewhat resilient to certain quantum errors, because we are not fully converting that into quantum. The partial is quantum, partial is classical. So somewhat this technique will resist with the errors. And limitation is noise. As I said, when you are dealing with deep circuits, so obviously you can't have the control of the qubit. Your qubit will be influenced by the environment, so noise will disturb your qubit movement performance. And barren plateau. So again, if the searching space structure is flat, then you can't find the best one, because everything looks like same. So you don't, when the cost estimation won't find the value for the next iteration. So your learning will stop there. You can't continue the learning. So that is another issue. And coming to VQE, variational quantum eigensolver. So mostly like this variational quantum eigensolver, mainly they are using for chemistry, quantum chemistry, for molecule molecule structuring, or constructing the new molecules like that. So they are using it, but they are also making use of this VQE for optimization also. It is also not only used for optimization, it is used as a classifier also. So this VQE circuit has algorithm have 4 main components. The first one is the operator. So that is nothing but your Hamiltonian. So what we first defined, like the initial state, what we are defining. So that is an operator. And then the quantum circuit and an estimator. So it estimates the expectation value. So here it should be 1H, by mistake 2H came. So the H is nothing but the Hamiltonian operator. And finally, we are using classical optimizer only. Only for exploring all the possible combinations of the solution, or all possible combination of the future space only, we are using quantum. And after we explode and we get the value, what is the correlation, or whether they are similar in terms of classification, we will find, we will construct a matrix, whether these two particular nodes are they are similar or not similar. So based on that, we will construct the value finally. So with that value, deciding whether it is belongs to the same class or not is a classical part. So the workflow of VQE is, again, here also we will find the Hamiltonian, the initial state, and initial parameters, the theta naught also will be set. Again, it is randomly chosen. So this part is the classical one. We are not using quantum there. Classically, we are finding some random initial values, theta. Theta naught is the initial parameters. Here, Like we will be using, sometimes we will be using it's a combination. Your quantum circuit is a combination of parameterized circuit and non-parameterized circuit. So parameterized gates and non-parameterized gate. So this theta values will be given to those parameterized gates. Non-parameterized gate, they will work as it is, like whatever state coming before, then it will do the corresponding transformation and it will give. Okay. And you will have these qubits will be fed to parameterized quantum circuits and state preparation will happen, and then the expectation value will be done through this rotation and this measurement, and this expected value will be given to the classical optimizer and it will generate the next value, next parameter to continue. So more or less your QA-OA and VQE are in abstract view, if you are saying they are same, looking same, but what they are doing the energy minimization. For energy minimization, they have two layers, the problem layer and mixer layer. The two layers are repeated again and again for many number of times. So like you have some estimation, right? So if I am starting the energy in this level, to reach that level, how many layers I need? So based on that, you will have the two layers are repeated for multiple times. Whereas here we have some quantum circuit, like the parameterized quantum circuit. Here we don't have the layered structure. In QA-OA we have layered structure. Here we don't have layered structure. So it will have the combination of X gate, C0 gate, like that. It will have different gates, like the rotation gates, RX gate, because like this theta and all, like we are doing rotation based on some axis. If I am doing rotation based on X axis, I will use RX. Rotation based on Z axis, then I will use RZ. So I will use those rotation gates, and also if I want to have the entanglement, then I will use C0 gate or ZZ gate I will use. And the advantages, the main advantage what I say is like this circuit based algorithm is very adaptable for different problem domains. It will work for quantum chemistry, it will be suitable for finance, it will be suitable for logistic, many applications it deal with. But when you are going for energy based system, mostly it is suitable for optimization problem. So that's what D-Wave, like they did many problems using optimization problem using that QA-OA, but after that they feel that like they are not doing good for other problems. So that's what D-Wave also is started to build their circuit-based quantum computer. So, but our Google and all, Google, IBM and all, they are developing the circuit-based quantum computer because it is having wide adaptability for different problems. The challenges in quantum optimization. So the noise is the very big problem in this NISQ era, barren plateau and limited circuit depth and qubit count, so that we can't move forward for the very complex problem. If we are really dealing with very complex problem, obviously we can't fit that problem with the less circuit. The depth of the circuit should be more. So if we want to execute that lengthy circuit, the coherence time should be more. But still we are not achieving any like a good thing, a good measure in that. Like still we are lagging at.
How much time is maybe I just how much
so that like it's based on like how much computation time we needed, like how many gates we are having like in that. So that's what like even we do publish papers in QML, but the feedback what we are getting is still there is no practical computer come and practical difficulties are there. How come you are telling that your computer, your research is achieved this much percentage of result like that? So the advice what they are giving us, go with some resource. Based on the resource, they are asking us to justify the outcome. So how many gates, like for a gate, if I want to execute a single particular gate, how much computation is needed? So in terms of that, number of computations needed. Classically, how many number of computation needed? If I am going with quantum way, how many number of computation needed? So people are asking in that way, like to compare. Theoretical, as of now, theoretically, like if you are designing a quantum circuit and if you are comparing your problem in terms of computation, so I am using these many gates. So this is my circuit depth, and within this computation I can achieve the result. So if we are justifying our result, that is enough as of now. But if we are saying like I am achieving 99% result over classical machine learning, no one will believe us. Then the next method is kernel method. So like the classical, generally the kernel is used in a situation where like if we want to classify a points, okay, so in a low dimensional space. So sometimes like in linear regression, what we do if we want to classify the points into two different categories, so we will have a straight line, so that's like we will form a regression thing, and it will form a straight line, so it will divide the points into two. But most of the time, so we won't have that kind of situation when we deal with the complex problems, because a single line is not sufficient to divide the points into two categories. So in that case, what we will do, we need to project the point into more higher dimensional space. In two-dimensional, like the points will look into the flatter thing. So we will look for some either horizontal or cross way, like we will try to have some line to segregate the points into two categories. But when you are dealing with complex problem, like if you are seeing the points in lower dimensional, it looks like flat, but actually they are not nearby. So your single line is not enough, like that regression line is won't divide the points into the category. So what we have to do is we need to project the point into higher dimensional area, 3-dimensional, 4-dimensional. Then you can clearly find out the space between the points where you can cut, so that the points can be classified into two categories. So that is the motivation of kernels. So mostly these kernels are used in the classification related problem. Okay, so the best example is your SVM. So here I gave the picture, right? So it's a 2D image. So here, suppose if you are having, if these points are spreaded in such a way that the red points are somewhere here, the green points are somewhere here, then through the linear regression line we can split that into two. But if you have this kind of situation, so this red points are surrounded by this green points. So here, whatever line I plotted here, I can't segregate these points into two different classes. So what we supposed to do, we need to project that into the higher dimensional. So if you are projecting into higher dimensional, then you will get the view. So this surrounding thing will come in the corner and these will be coming in the center. So you can see this face, this projection, then you can say that this is the cutting point. So this clarity you will get it when you are projecting the points in the higher dimensional. That is the role of kernels. So classically speaking, the classical kernels, like they are struggling a lot when you are projecting the points into higher dimensional, because the computation is growing exponentially. When you are 2D, like a 2D matrix, it need n square thing, right? If I am doing a 3-dimensional, it is n cube. Like that, it is going on exponentially if I am increasing the dimension. And the data points, it's also more. You just imagine the computation time. So it is not practical for a classical computer to do that. So we are using quantum kernels here. So here the classical perspective of kernel is given. So it maps the data into higher dimensional feature space. In this higher dimension, complex patterns become linearly separable by a hyperplane. So instead of plotting a line, through the hyperplane, we can divide the points into the different classes. So here the similarity between the sample is computed using a kernel function. Here, how the similarity is calculated means through the inner product of the 2 points. Okay. So as I said, the limitation of classical computer is it struggles when the dimension is getting more and more. Then coming to quantum future map. So like it operates based on the Hilbert space, right? A Hilbert space is having enough number of states, like unlimited number of states are there. So which scales exponentially with the number of qubits. Like if you are increasing the number of qubits, you will get lot of space to represent the points. And everything you can deal with parallelly through superposition. If you are using 2 qubits, 4 states you can explore simultaneously. If I am using 10 qubits, 2 power 10 states I can explore simultaneously. Okay. And then, so the idea is here the quantum processor, like use the quantum processor to map the classical data into this Hilbert space. And here encoding will be there. Here the data is converted into unitary operations. You know the purpose of unitary, right? Why the quantum gates are unitary? Because all the quantum circuits are reversible. Classically, all the circuits are not reversible. All the operations are, if you do any state transformation, you can't revert back to the previous state. Whereas in quantum, you can do that. So for that only, like all the gates, all the state transformation, everything needs to be designed as a unitary. So here we are mapping the classical data into the quantum state. And here, like the thing is, we are mapping the future, that is the unitary matrix to a particular state, KET0. Right? Here we are going to find out the similarity between the points. So I assume that like I am initializing that to the state KET0. Okay? And I will explain how it works. So defining the quantum kernel. So it's nothing but the similarity between the 2 points. Okay. So if I compare the similarity between these 2 points, like it's a similarity between the point X and Z, if they are similar, then their overall probability, that is modulo square, should be equal to 1. Okay. And how they are implementing here is, if the states are identical, the overlap is equal to 1. If the states are orthogonal, that is completely different, they are cancelling out each other, right? So then you will get 0. Okay, so this value, like this value of 2 points, if I am comparing, means if they are similar, I will have 1. If they are dissimilar, I will have 0. Like this, I will form a final matrix. The similarity matrix, I will have it. Then I will give this matrix to the SVM for classification. So the task of SVM will become simple now. So here in which phase we are introducing the quantum? We are introducing the quantum in raising the data points to higher dimensional, exploring the data points in the higher dimension, because that is the problem in classical kernel, right? They are struggling in that. So only that portion alone we are replacing here. Then the SVM task, the classification thing, it happens as usual in like normal SVM. So then how to compute the kernel? So we cannot calculate the overlap mathematically, like we must measure it. So we are here, the strategy what we are following is compute and compute strategy we are following it. So first we are applying the unitary u of x to the state KET0. This is the initial thing what we do is like the classical points are mapped to the quantum as a unitary representation, and we are initializing those points to the state KET0. This is the starting thing, and then apply the inverse unitary of the second data point. Suppose if I want to compare x with y, so x I mapped that with some KET0 value, and then like if I want to compare the similarity between the point x and y, then what I will do, like the y unitary matrix, I will take the dagger value. So you know what is DAG, right? U DAG. Okay, so it's a complex transpose of the complex conjugate. Okay. So, if I am then to compare the next point, we are applying the inverse unitary of the second data point, U DAG Z. Okay, so here the point we are comparing is Z. Okay, then measure the probability of returning to all the 0 states. Right? Okay. Okay, okay. So I have one code, I cracked the errors of one particular code, remaining codes I couldn't able to make it because every day the Qiskit is modifying, the previous functions are depreciated and they are giving different modules and different methods. So these programs we run it last sem, but now I am trying, it's not working. So for QSVM, like I said, no, like the steps I will explain here. Why it is not? So the fundamental libraries you need to include as usual. You need to include install the Qiskit and AR simulator, whatever the necessary packages you need to include. Then here we are adding up the generating the data set. Here we are taking the make moon data set from the sklearn data set, and then we are giving the details like how many samples we are taking, the noise and all these parameters we are setting out. So here we have taken 100 points, 100 samples we have taken from the data set, and just we displayed like how many what are the features, that is how many features we have taken. Why it is not moving? And then after we define the including the data set, so we need to map that data into the quantum way, right? So for that we are using a Z feature map here. So it's a simple encoding scheme. Because why it is simple means it won't use any entanglement gates here. When you are using entanglement and all, the computation will be more and it looks complex. So here the Z feature map is using a simple gates. Okay, so simple rotation gates which rotates based on the Z axis.
So while using the gates,
Qiskit only, Qiskit only. No, we are using with I am running in Colab only. Okay, I am not using IBM processor because it's costly. Only for IBM summer school and all, that time they will give some credits to us. So for we can use the processor in a minimal rate at that point of time. So after that they will close that concession. So otherwise we need to pay and get it. Then by using this Z feature map, we are converting that classical information into the quantum one. And once the mapping is done, we need to import that fidelity quantum kernel and this compute uncompute method strategy I explained, no? So to calculate the similarity between 2 points. So we are importing all these things. Everything is there. Only thing is we should know what we have to use. So that's it. So that too, your Gemini, here. Earlier, this Gemini is not included in this quiz kit. Now, the thing is it won't give the correct answer at this first stretch. We need to keep on refine, and we need to, that only we are doing because they are keep on changing. We have to read the discussion forums, and then getting the help of this Gemini AI, then only we are converting our code for every semester. Because we introduced all the courses as a J course. Its lab is there. So this code also again we need to work. We need to resolve all these things. Yeah, this QSUM is working now till the, what to say, I got the accuracy. During the first run, I got a 65%. For the second run, I got 60. But visual representation, it is not, it's taking much time. From the morning I am running, it is not completing. I will share this code to you, and also I will share your code of VQE and QAOA. But that was worked last semester, but now it's not working, but you try with the help of AI. It's random, it's and all like, what to say, synthetic data sets. Because dealing with real data set, it consumes more processing time. So for the students, like to use this system, like the processor of our laptop, like only this much is enough.
You're running this collab only. So then when you want to see, for example, IBM simulator. In IBM simulator, how we can integrate this program?
IBM, like the simulator version, like the picking and dropping and all, the composer and all, like only circuit alone you can build. Code, like they removed that one. So only possible thing is you need to get the processor, IBM processor, by paying the amount. You have to submit your code to them, and your job will be in a queue, and whenever the processor, your term comes, the processor will execute and the answer will be there. Like you have to fetch the answer. Yeah, then only you can execute your code in the processor.
So there we can get bits. By using bits, we can't run.
No, if you want to get the actual result, then you have to execute in a processor, quantum processor. So if you are going in a simulator, so if you want to publish a research article, the simulating result they won't accept.
Then we need to share this completely with them.
Yes, in that way you have to do. That's what, like if you are getting any fund from any professional bodies, and if you are giving this requirement as using this quantum processor, so they are not, even though they are not sharing it as a money, they are giving it as a credit. They are giving AWS credit, and this IBM, they are giving it as a credit for a limited period.
But that is what man is telling you. What would be right?
Yes. They are like now for making their product familiar, they are giving all these things, like how IBM did. Earlier they did, because when we introduced the course at the first time, we did it in IBM Composer only. Like we did the code there directly. But after that they removed the free version, then we are using this Colab.
This program explanation also, you've done any documentation so that you can do that this HKBK something. Yes,
Here it's given no, like the text also I have included. So before going to the next block, I gave the text as like what is the role of that particular block. Even if you can ask the help of Gemini, it will explain line by line, line by line.
Ma'am, in each semester they are this one subject you were telling for students also. In which semester it's
Every semester we are floating this subject. Every semester we have quantum computation, quantum machine learning, and quantum cryptography. We have. Yeah, we are floating it as an industry elective. We are also floating minor degree this semester we started, and honors we started last year. Honors in quantum computing. After 4 o'clock, the class will be. So still 7 o'clock we have to stay and take the class. So this code I will share it to you, you go through it, and the remaining code also, if you are giving time, I will clear the errors and I will give you I will forward the working code to the coordinator. Yes. PPT I will give to ma'am. Okay. Yes. So I think with this kernel, I think I finished. The hardware limitation, like considering the hardware, like the limitations are, we need to keep the quantum computer isolated. It's a we need to, most of the people, they are keeping it in a noise free environment. In our college also, they are building a quantum lab, in the quantum optics lab in that way. If you go and visit CDEC Pune, so they are all. Huh?
Yesterday we went to see that. They also they were showing that.
Yeah. Like they will be like keeping the processor in mostly in underground or somewhere else where the noise disturbance will be very less. So that is one of the limitation, and another one is quantum decoherence. So if we want to deal with the complex problem, obviously we need to construct a lengthy circuit. So if we want to deal with lengthy circuit, the coherence time should be more, but still we are lagging that. That is the another problem. And then rotation in quantum computers, because it's an iteration, like these circuits won't be completed in a single run, we will be repeating it for multiple times. So here there is a possibility of if we do any wrong rotation, it will disturb the quantum states. You will lead into the wrong thing. Wrong rotation can cause an error in the output. So these are the hardware limitations of QML. And the challenges, already I said, limited qubits, noise and decoherence, high training cost, and unclear quantum advantage. Still, we don't have clear idea in which phase we need to include, which property we need to include. So it takes time. So with this application area, it's not limited. You can try different environment. Wherever it's possible, you feel you can try implementing this QML. That's it. Yes.
So that is do we try to share some stock exchange
portfolio? It's based on like the credit scoring also. They like we are using how much different aspects they are using, sir.
So especially portfolio in the sense
like for finding the best customer in different aspects.
So that is
yeah. Drug discovery, like practically, like they will try different combinations of different chemicals in different proportions, and it's like a trial and error. So if we are lucky enough, we will get the medicine soon, and or otherwise even 10 years, 20 years also, still we couldn't able to find the medicine for a particular diseases, right? So here, like if we are going in quantum way, we will explore multiple combinations parallelly. So there is a great chance that we can get the solution soon.
anyone for example, Google has already has quantum computing. So is it actual data they ran and then they get the results? For example, any finance or story.
Still, they are not coming into the application side. Like they want to build the thing, right? If they are ready with the real quantum computer, through that they want to make the money, right? So still they are working on enhancing the performance of their computer. So still they didn't turn to the application side. because they have very supercomputers to deal with that. So still they are not much concentrating on this application side. So that's all from my side. Thank you. Thank you. So this is a book, Sir Maria should for quantum machine learning. In IBM Qiskit also you can have study materials. Like there mostly they will discuss about the methods, what packages needs to be used. Their discussion will be in that way. No, it will be like only in Qiskit you can do, but what people are feel is that instead of going with Qiskit, Pennyline is having more advantage in working with QML. They feel that it is easy to work with Pennyline more than Qiskit. Pennyline. Yes, ma'am. I will come there.
Signature and today's center.